Shang, this is showing red. Showing, no, this is okay. All right. Welcome to the second day of the CHAM++ workshop. It's my pleasure to begin this day with a keynote speech by Vivek Sarkar, who is a I better not butcher this. He's a professor and chair of computer science at the Rice University. He's the no, I forgot the initials. Butcher, professor of computer science. RE? No, I forget. Anyways, well, and thank people who endow these things. So ED Butcher. I had these initials in my head. ED Butcher Chair in Engineering. And I knew Vivek from many years ago, mostly from his time as IBM research, where he was in charge of the. There might be a formal position, but he was involved in charge of the productivity aspects of the HPCS, the productivity, the DARPA project aimed at improving productivity in parallel programming. He was involved in development of X10. Probably prior to that, the JIX runtime system, and his expertise in compilers is well known. He graduated from IIT Kanpur with his bachelor's, master's from Wisconsin, then PhD from Stanford, and so on and so on. There are many other things that I could mention. He's a fellow of the ACM. And he's now leading this OCR effort that we'll probably hear more about. That's an open community runtime effort. So without further ado, Vivek.
Okay, thanks, Sanjay. Thank you. So I remember when I first joined IBM, Sanjay invited me to visit, and maybe 1989 or 1990. Was your group called PPL at that time too? Oh wow! And at that time, Sanjay's mind had many things. It had the CHARM-related stuff, but he also would talk about functional programming and logic programming, and so we had lots of good discussions that date back a long time. Lots of good arguments too. So acknowledgements to the team. There's the work that I'm going to present is really obviously contributions to the team. It's a good group that works together in terms of research scientists, postdocs, and graduate students. And of course, to us, acknowledgements to our sponsors. So just to set the stage, and everyone here knows this, for about 7 or 8 years now, we've had a good sense at a high level of what's coming in terms of extreme scale systems. So I had the opportunity to lead this DARPA exascale software study in 2008, 2009. And very early on, we decided to refer to these challenges as extreme scale rather than exascale because we saw them occurring across the board. The changes were, the fact that your building blocks, the chips are going to be, and have already become massively multi-core, homogeneous, heterogeneous, performance driven by parallelism, constrained by energy. It's almost, and we've heard talks related to that, like a bin packing problem almost, and resilience issues. So these were the key challenges, and that's really guided our research and many of the research of many other people in the community. So the question is, today's talk I decided to focus in the time that I have on hybrid programming because that comes up as a pain point. You hear of people, really struggling with combining message passing and task parallelism, with combining CPU parallelism and GPU parallelism. So the word hybrid is used for all of those. So I looked up, I wanted some interesting images because I don't normally put interesting graphics. I looked up Wikipedia and found some interesting hybrids that apparently were actually bred. There's a zebra and a donkey, a lion and a tiger, a jaguar and a lion. So the thing is, you can do cool stuff, you can build, but I think our goal is not to build one-offs. We want to find solutions to hybrid programming that would really lead to a more sustainable ecosystem rather than a one-off demonstration. So I think what is considered to be hybrid depends on where you start. If you start with a very, very limited model, let's say that is bulk synchronous SPMD, notion of fixed number of ranks, then many things turn out to be could be viewed as hybridization. Just even asynchronous data movement, or task parallelism within the rank, or adding accelerators, or trying to do migration. These all appear to be extensions that are somewhat different from your starting point, and then you have to work on kind of banging heads together to make it all work. On the other hand, if you try to go for something that's hybrid by design, which I think is also the goal of the Charm++ project, the idea is that you look for some unifying principles, so that once you have these unifying principles, then the combination of features just work out naturally within the same framework, and you have semantic guarantees that come about from the combination. So some of the same things earlier can actually become easier, and I'll show examples when you have a unified model. I didn't find a good graphic for the positive hybrid by design. There must be one, so the best I could come up with was like an early Prius thing. But that's an example of something that was hybrid by design rather than hybridization, which might be, okay, go put a battery in your back seat or something. Okay, a related thing that many of us in the community have discussed is that who's our audience? Well, the developer community is very large, and in many working groups we've had this inverted pyramid, sometimes with 2 or 3 levels. So there are domain experts at the top who really just want to solve problems. And they don't want to care about parallelism. They have enough challenges as it is. There are concurrency experts at the bottom that use low-level parallel programming models and actually relish in all the fine-grained details. You can have entire PhD dissertations on non-blocking queues and things like that. And in any ecosystem, a critical role is played by the software engineers that bridge the gap. This is exactly what happened with object-oriented programming too, where the bottom of the pyramid might have been, the compiler or the implementers of Smalltalk and C++, and the software engineers are the ones who built a lot of the frameworks and enabled a lot of applications. So we've been guided by that as well, and our goal is to try to find unifying principles, but we focus much more on the upper levels. And this is not drawn to scale, at least not to linear scale. One could argue that's at least log scale in height in terms of the numbers of domain experts, software engineers, and concurrency experts. And some of our experience has been, in this execution model that I'll share with you in terms of the primitives. Those can be directly available at this mid-level in languages like, and we already have them available in C, C++, Java, Scala. But an area that we really want to explore more is higher-level frameworks on top of these primitives. And so far, our experience has been in our collaboration with Kathleen Nobe and others at Intel on the CNC project, where we've created environments of domain experts where they could write steps in MATLAB or Python and so on. Okay, so here's the sort of the context for our group's research. We focus really on the programming models, compilers, and runtimes. To a large extent, the application work and the hardware work are like boundary conditions for our research. It's really been great to see the work in PPL with very, very active involvement with applications. We don't have that level of involvement, but we have some. Sitting in Houston, we've now begun interacting with local oil and gas companies and also with the medical center. And so our engagements tend to be folks more on the mid-level parallelism stage, not the very high end of supercomputing. But obviously, we're interested there too in our work with the DOE. So there are these primitives that I'll talk about, and our goal is to bridge the gap using these 2 levels of programming models. And we've also experimented with a wide range of hardware, and in our effort to try to really push the boundaries of what could be done with hybrid approaches, we want to look for things as diverse and heterogeneous as possible. One that I'll show you results for is where we were able to have FPGA, GPU, and CPU cores all in the same platform addressed by a unified programming model and runtime. Okay, so what are the elements? And this has been gained over experience. at the highest level, and this is really our goal, is to come up with this unified model that can map onto this wide range of extreme scale platforms, not only what I showed you earlier, but what we expect in the future. So we believe that asynchrony is key, and and that's something that Charm++ I know believes in also. So have primitives in the execution model for creating asynchrony tasks, terminating, waiting for sets of tasks, and data transfers. A key belief for us in this unification is that data transfers and computation should really be treated on par, and you'll see examples of that. Then locality control, which really is generally computation and data distribution. It can apply to clusters, but it can apply to even within a node and cores within a chip. And a global namespace plays a key role over here to allow for the hierarchies of memories, like we heard from Bob Wisniewski yesterday, with non-volatile, volatile memory, and so on. And finally, these tasks often need to interact with each other beyond the termination. If the tasks are small, very often the interaction is that you just wait for them to complete, and that triggers a new event or some new ability, but very often there's a need to do other kinds of operation. And there we've split it into two parts, a mutual exclusion and a collective and point-to-point. So I won't have time to talk about all the primitives, but in general, this is how we frame it. And as an example, and this is what I use in my class, if you take something like a CUDA kernel invocation, that seems somewhat different, and adding it to your model is hybridization. You have to do this triple angle bracket thing. In our model, well, a CUDA kernel invocation is just an asynchronous task invocation at some other place, and the body of the kernel is two levels of parallel loops, where the inner parallel loop is phased, meaning that it can have barrier-like phases. And of course, CUDA has specific notations for all of this, like sync threads to the barriers and block ID and thread ID, but that's really the abstraction. And then all the properties I'll show you will follow for this as well. So here are some of the properties and why we see benefits in taking this approach. Sometimes people get into religious wars saying that you can express any algorithm or any application in any programming model, and that's kind of like the Turing machine TARPIT kind of thing. And I believe that is possible. You can give people threads and locks and they can do everything. But the question is, what semantic guarantees do you have? Just like type systems give you a rich set of semantic guarantees, I think these primitives also do that. So one is the primitives, like for instance, using something like finish or Chapel's sync or even Silk's spawn sync and other primitives guarantee deadlock freedom for a large subset of operations. In fact, we have only very specific operations that are really advanced features that could potentially cause a deadlock, such as explicit wait in phasers and explicit wait in async. Data race freedom is much, much harder to guarantee, but there are certain cases like values in futures, values in accumulators. There's some work we did on read-write permission regions, there's isolation actors. These all guarantee data race freedom. Determinacy, and this is something I've had the opportunity to discuss with Jack Dennis at great length. We wrote a paper also with our definition of determinacy, which includes both functional determinism and structural. Structural means for the same input, you'll always get the same computation graph, and not just the same output. And it turns out data race freedom implies this powerful determinacy property for a large set of constructs, but excluding the mutual exclusion. So it turns out isolated actors are very elegant ways of getting data race freedom by default, but those constructs actually, we believe, are primarily should be used if you intend to have non-deterministic computations. And there are other things like accumulators and other properties other constructs that can give you determinism and data race freedom without getting into isolated actors. And then the point is, we don't want to just come up with the lambda calculus of these primitives. We want to make sure these primitives are capable of being implemented efficiently. And our work and a lot of other related work has shown that these primitives can indeed be implemented efficiently and also integrated with each other. So here's another way of looking at what I just said. That is, if you can classify programs as deadlock-free, data race-free, determinate, class where data race freedom implies determinacy, and serializable, meaning where you have a very simple transformation procedure to convert your parallel program to a sequential program with one possible semantics for your parallel program, or equivalent semantics, let me say, but one possible execution. And so, for instance, the Silk folks had advocated this for a long time with the elision property, saying you remove the spawn and sync, and you can debug a sequential program. So we can see that, you know, if we use these async finish future constructs that are task termination, creation and termination, you're in the serializable set. Adding barriers actually loses the serializability. So as you add more constructs, you get more generality, but you lose some semantic guarantees. So the reason is, if you can imagine a for loop with a million iterations, phase 0, barrier, phase 1, and you say, okay, let me throw away the parallel loop and the barrier and execute it sequentially, that won't be a correct execution, because iteration 0 will do phase 0, phase 1, iteration 1 will do phase 0, phase 1, and so on. You have to transform it in a different way by distributing the loops and so on to get an equivalent sequential program. Yes? Yeah? Oh, sorry, the plus is put parens around DRF implies det is one term. So the it's not DLF plus DRF implies determinacy. It's you get deadlock freedom and the property that data race freedom implies determinacy. So I should put parentheses. Okay, good. Yep. And then if you then add this data-driven tasks, event-driven tasks, which give you more generality, you use the deadlock freedom because you can create tasks that wait for events that never show up, and you can argue whether that's technically deadlock, but that's a form of progress, the lack of progress, that's like deadlock. And then, of course, if you restrict shared accesses, you get data race freedom, and they don't all perfectly nest. In particular, you know, you can see this is data race freedom, but determinism slices through all of them. You could have programs with data races that are deterministic depending on your memory model. Okay, the other thing that I really enjoyed doing after moving to Rice is develop this undergraduate class, which is now taught at the sophomore level. It's taken by CS majors and non-CS majors. And the approach is really to introduce them to the primitives. Of course, if I really want to do something for the uppermost part of the pyramid, we could just teach them something like MATLAB or LabVIEW and let the tool chain take care of the parallelism. Here they're learning about stuff under the hood a bit, where simple things are simple, but complex things are also possible. And they learn about all these constructs. Now, for these people, they haven't even learned, they haven't taken computer architecture, they haven't taken operating systems, they don't, in our curriculum, at least at this stage, they haven't learned to program in C. So this class is taught using, you know, a Habanero extension to Java, but we could imagine this material being taught with something like a Habanero C++ as well. And I've now begun creating short videos, like 5 to 7 minutes for the different principles. Okay, so now having said all that background, let me just give you a flavor of some of the primitives and try to get at the interesting hybridizations, because that's the focus of this talk. So task creation and termination, there's different kinds of notations. I'm using the one that came from the Extend project, where async creates a task. So it's just like, and then finish has a scope, and at the end of the finish, you wait for only those tasks to complete. So it's a little different from join all or from Silk sync, which just joins for everything in the past that has been created. You can nest finish and async as deeply as you like, and the scope is always very clear, because every async has a unique dynamic immediately enclosing finish, and that's the one that waits for it to complete. Now, one thing, and this will come up later when we start looking at communication, this async could be a computation or a communication. So if you send out a whole bunch of non-blocking messages, and we have an example of that when we integrated Habanero C with MPI, the finish will wait for all the non-blocking messages to complete before going past it. And getting back to the properties, even though finish is a synchronization, it's a restricted kind of synchronization, so you cannot create a deadlock cycle with it. And the way to think about it is, if you think of the task creation tree, finish is always, you're always waiting, always have an ancestor waiting for a descendant, so you cannot create a cycle. Okay, so something happened. So here's an example of, and I'll show you examples with both Java and C as the talk proceeds. So this is an example that I teach in my class of this parallel spanning tree, not minimum spanning tree. They do a parallel minimum spanning tree later also with Baruch's algorithm and so on. But this is very simple. Just do a depth first traversal, and when you're done, the input is every vertex has a list of undirected graph, list of neighbors. And when you're done, every vertex has a parent. That should be a spanning tree. If you do the elision and just ignore the red stuff, you have pretty much a sequential computation where you call compute on root, visit the neighbors, you try to become the parent, try to make each neighbor the child in the spanning tree. If you fail, then you just go to the next neighbor. If you succeed, then you call compute on child, and so on. Now, for the parallel version, the main insight is that when you're visiting all the neighbors, you could do that in parallel. So we wrap this in async. By the way, this is the new lambda notation in Java 8, in case you haven't seen it. And I think this makes things also more synergistic with C++, which now has lambdas as well. You put a finish, and this shows how it can be interprocedural. The finish is right at the outermost level. You just want to wait for all the asyncs to complete. In this computation, you don't need to wait level by level. But in a model like Silk, or actually even OpenMP, you require parents need to wait for children. So the waiting would go level by level up rather than just once at the root. And one of the tricky parts over here is, and this is a non-deterministic algorithm, because for the same input graph, you could get different spanning trees as output. The tricky part is coordinating this access where there's a shared field. Two vertices could attempt to be the parent of the same child, and one of them has to succeed. So isolated, and we'll talk about object-based isolation briefly later, where this is with respect to this object. And a clever compiler can actually recognize that this matches a compare and set instruction, and you can implement the semantics that way. So this gives you a feeling of how things start composing. There's a notion of escaping asyncs, which means the method can return before the async completes. If you don't want that, just put the finish around the method body. Yeah. Oh, this is this child.try labeling this. So what you're saying is you pick a neighbor, you want to make it your child in the spanning tree, you call try labeling on the child, and this is n is the node that's attempting to be the parent of that child. So once you call try labeling, this is the child over here, and n is the node that attempts. Yeah, we can talk about it. And the business about final is only because Java 8 lambdas require these any locals that are outside the scope to be effectively final. You don't always have to have a final declaration, but that's sufficient. Okay, so now let's expand the aperture a bit and talk about event-driven or data-driven tasks. Yes? Sorry. Yeah. Oh, okay. Yes. So the thing is, how you prove it, so that I think is challenging. So this intuition over here is that all shared accesses occur in isolated. Well, you could have a type system, and we've done this, we have a permission-based type system, for example, so you could do that, right? No, what I said was, yeah, I said, well, two things. One is data race freedom implies determinacy, and then how do you guarantee data race freedom? if you restrict accesses to futures, accumulators, isolated actors, all your shared accesses. Now, how you restrict it depends on a combination of the programmer, the programming model, type system, and so on. Well, it depends on the memory model. So, yes. I'll get to that at the end of the talk, because then we can have, otherwise we'll enjoy the rest of the talk. So it depends on, but the point is you have, yeah, I'll get to that. So now let's extend our notion of tasks towards these event-driven or data-driven tasks, which really actually capture a lot of the hybrid capabilities that we want, because when you offload a GPU kernel, you want to be notified when it's terminated. When you initiate a data transfer, you want to be notified when it's terminated. So the model is, and now I'm switching to C-like syntax, we have it in both, where you have an async, but you have preconditions to say that this task can only start executing when some events, or what we call data-driven futures, for historical reasons, become available. And we really want determinism with this construct. So we require that these data-driven futures are single assignment, or you can think of it that, single assignment events, which can be triggered by any task by doing a put in this data-driven future. And then within the body of the await, within the statement, you can do gets in the data-driven future, but no blocking is needed at that point, because you would have already done an await. And in fact, in our Java-based implementation right now, we have an exception if you attempt to call get in a task without having done an await on it. Okay, so what can we do with this? So here's an example of a Smith-Waterman tiled version, simple dynamic programming, where what you want to do is, rather than get into explicit wavefronts and parallel loops, just specify the dependencies. So the way you would specify the dependencies is you break it up into tiles. I'm not getting into the computation in each tile, that's in compute. And each tile is an async await that waits for the DDFs corresponding to the three predecessors according to dependencies, above, left, you left. And then you do a put on your DDF. One interesting thing, and this comes with the power of the model, is you could run these loops backwards also, and the semantics would be exactly the same. Your performance may not necessarily be the same, but the semantics would be the same. You're creating a bunch of tasks with dependencies, and this is a question I often give my students in a quiz or midterm, is, will the thing terminate if, for instance, I went from H to H minus 1 to 0, J went from W minus 1 to 0, and that's fine. You're just creating tasks backwards, but each has their dependence. When the first task executes, it then releases successively all the other tasks. Yeah. So this all fits under category 1, just to say this is where we create asynchronous tasks and coordinate them. So these are primitives. You saw finish, you saw async await, and they have different places in that Venn diagram. The second category of primitives that we have relate to locality control. And primarily, I mean, when this is still a subject of ongoing research, but right now we're primarily thinking of these as tuning hints. That is, they are separation of concerns. The locality annotations don't change the meaning of the program, but could have a huge impact on the performance. And one of the abstractions that we use to guide this is this notion of a hierarchical place tree, which is really an abstraction of that's convenient for both the hardware and the application. And in fact, you could explore multiple HPT configurations of the same hardware and application, and certainly different applications might want to view the hierarchy in different ways. So let me give you a little more of an operational view as to what it does. So there's an at clause for an async that is trying to give some affinity. Now, in the hierarchical place tree abstraction, we are abstracting the machine as a tree, and the at is logically saying put it in a queue, though it's not a first in, first out queue, like a set of tasks to be executed at some level, and at least for now, the policy that we have is that a worker only picks up tasks from its ancestor places. Now, with that policy, the way the locality control comes about is if you put a task somewhat higher in the tree, like at the root, it can be executed anywhere, so it's better suited for load balance, but it doesn't really have any affinity. Whereas if you put a task, let's say, in place 2, it can only be executed by these 2 workers, even if those other workers happen to be idle. Now, people in my group are exploring variations of this, maybe where an adaptive runtime might percolate this up, and even this hint can come from the compiler. We have some collaborations with Reservoir Labs where they're looking at compiler generation of these hints, and of course could come from the programmer. So this is just some work from a thesis that was recently completed by Sanjay Chatterjee. And one of the things we find is that the impact of these annotations is a little harder to measure on today's hardware, but our belief is going to become more and more important in the future. And certainly we see bigger impacts when we count cache misses compared to just measuring time. So this is a tile Cholesky, and something happened with the PowerPoint going from Mac to Windows, I guess. But this is a tile Cholesky example where the baseline is the blue line and the red line is hierarchical place tree. Same computation, but just an affinity on where things should coexist. With a large enough tile size, like 125, it's really compute bound but as you get to smaller tiles, and we believe this will be a trend in the future as the numbers of cores increase, we could see a bigger impact of locality, and that makes sense when you have smaller tiles, that execute for shorter amounts of time. The opportunities for shared cache reuse increase. Just to give you a feeling how this could be done, we've also experimented with some mini apps, including Lulesh. In Habanero C, what you can do is, the place is just, it's a notion, what you can get from a place is you can get, anytime a task executes, it can capture its own place, maybe store it. So here we are assuming that the user has some function that returns a place where a tile of iterations like I out to IN may have been executed in an earlier call. We say we want to bind it at that same place, which may not be the leaf, it may be some mid-level. And this reuse can take place across loops and different functions. And so even though there are compilers that do locality optimizations, when you have large applications with loops spread across many procedures, these kind of affinity hints can help. And again, for Lulesh on today's machines, we see a little bit of a benefit. This was again on the 12-core machine with using places. We see more significant improvements in this case in the L3 cache misses. It's 1.5 times, well, in the unoptimized one has 1.5 times the number of cache misses as the optimized one. For some reason for this setup, we actually saw an increase in TLB misses. So that's the kind of thing that we're in the process of figuring out. If anyone is really interested in these memory hierarchy details, let's talk later. Now, once you've got this hierarchies, it's just another step to think about heterogeneity, where you can think of some places as heterogeneous. And like I showed earlier for the CUDA kernel, the async at notion can be extended for heterogeneity, and you need the compiler support to do the copy in, copy out of appropriate data, the explicit data transfer. I don't have time to get into the details of the runtime, but there are these proxy agent workers where we use CPU cores as workers that communicate with the GPU devices, and we can do work stealing across GPUs as well. Okay, so looking at some example, this is in our collaboration with UCLA and others in our NSF Expedition Center for Domain-Specific Computing. I'm just going to look at 3 stages in the imaging pipelining: denoising, registration, segmentation. And this is just and actually this work was done by taking CNC and mapping it onto our primitives. So a CNC program has graphical specification. This is a textual representation of the graph. The student leading this work added some annotations to say what, again, these are tuning annotations for each step. There could be multiple versions available. Denoising has CPU and GPU versions available. Registration has GPU, FPGA, and segmentation only has GPU. The numbers are not really significant other than there's a preference to run the step on the device with the highest number. And here are the dependencies, and here's a schematic of our runtime where these tasks are created. Essentially, async await captures the CNC model because CNC is all about creating tasks and making the dependencies explicit. And you know, we have our runtime has queues for and allows for cross-device stealing you know, when there are multiple versions available of kernels. And so this was evaluated on one of the test beds that I mentioned, where we took a Conway node, which has a very nice integration with FPGA and CPU compared to just sticking a Xilinx card because they share a memory controller. And then, but we added a GPU to it. And one thing we observed was the static schedule, meaning just obey the highest number for each step. And this is a very simple dependent structure, actually, not even like Cholesky, where you have 10 independent images, and each image has a pipeline dependency. So from denoising 0, registration 0, segmentation 0, denoise. So if you do that, then the schedule ends up looking something like this. I'll show you some more details in the next slide, and ends in something like close to 190 seconds. If you allow for that dynamic inter-device work stealing, we're able to complete sooner. And the details are over here, where now here we get into a bit of the details of our runtime, where the fact that we use designate a core to be a CPU core to be the proxy for the heterogeneous device. So if we just run that workload on 4 CPU cores, we get a completion time for those 10 images of 2200 seconds. What I'm showing on the right-hand side is a very crude estimate of energy, which was just obtained by taking the active time for the device, multiplying it by the power. We are now using things like RAPL and all with our collaborations with Intel. But you know, there's some estimate in kilojoules for doing all that work, close to 70 kilojoules. Add the GPU, significant time reduction, and energy reduction. And many people believe that the first path to having lower energy is get the job done faster, race to halt. Then hybrid CPU and GPU, you get a slight reduction, not a lot. But we're using 3 CPU cores because 1 CPU core is tied to communicating with GPU. We don't expect this to be an issue in the future as we go to tens and hundreds of cores. Then if you use the dynamic schedule, we have 129 seconds. The static one, as I mentioned earlier, has a longer time. However, the estimated energy is lower because the static schedule was, the GPU was the highest, had the highest power consumption of all these devices, and FPGA was particularly energy efficient. And what the dynamic schedule did was ended up taking some of the FPGA tasks and executing them on the GPU as well. Yes? Okay, so the representation is, and I don't have slides on that, but I can, so the way CNC works, and I assume you've heard CNC talks before from Kath, is that you specify your program as a graph that looks like this. And you have a tool chain, a little bit like your configure, or whatever the CI file is called in Charm++. From that graph, you generate a whole bunch of header files and so on. And then the user provides the essentially sequential code for each of these steps. Now, the question is, how do you get the FPGA and GPU versions? So in this collaboration with UCLA, Jason Kong's group has done a lot of work on synthesizing FPGA code from C, so we use that over here. And we have also done work on generating OpenCL from Habanero C. So that's how it would work out. There are some optimizations, yeah. and there's some tuning, yeah. But this, at least in terms of the coordination, so there's performance tuning you can do to give hints as to what data should be stored in. It's CNC or async await, depending on your perspective. Yeah, they really have identical semantics. So if you like the coordination language approach, you can use CNC. If that messes up your build system and your make file, you can use async await. Yeah. So, okay, so now let's go to the other level of the hybrid pain point that people usually talk about is, you know, the classic, how do you combine OpenMP and MPI and so on. So in our model, we've done this work recently of this, yeah, and it was mentioned yesterday also in one of the talks, is in combining, integrating Habanero C with MPI. So what we'd like to do is take the primitives and then look at MPI operations, like especially the non-blocking ones, MPI send, MPI receives, just like asyncs. So when we have a finish over here, we've launched some computation S1, we've initiated some communications. We could have one of the communications could, you know, have this request, standard MPI request, and we can use an MPI request as also one of the preconditions in async await. So what this means is that whenever the receive is completed, it'll trigger the execution of S2. We don't need to do our own polling or MPI wait and so on. That's all taken care of by the runtime. And S3 is something that can run in parallel with all of this. And finish says, let's just wait for that whole caboodle to complete and then move on to the next thing. How it's actually implemented in the runtime to help with the unification is we have, first of all, for the malleability, we have, you know, the computation workers and classical work stealing, so the number of workers can grow and shrink as much as you like. And we're doing a lot of some recent work on that related to energy optimization. And then we have a communication worker where one communication worker can serve some number of computation workers. And this is similar to the communication engine idea that you heard about yesterday. And so the communication worker is responsible for interacting. And in fact, when we run with MPI, MPI really thinks that we are running an MPI thread single mode. And it only knows about the communication worker because that's the only thread or performing MPI calls, whereas actually we have all this other task parallelism going on that MPI is oblivious to. And the number of communication workers and computation workers is also a tuning parameter depending on the network bandwidth, you know, what degree of parallelism you want in terms of injecting communications into the network and so on. And so one of the benchmarks that we tested in this synthetic kernel, unbalanced research, just because that's irregular, there's a standard MPI implementation that does dynamic work stealing where the programmer quite tediously, you know, use MPI messaging to steal work across MPI processes. And that's our baseline. And then what we did is, we obtained these results on the Jaguar computer before it was replaced. So we went up to 1,024 nodes and up to 16 cores per node. By the way, the PDF file should not, or if it does have these quotes and stuff, I'll replace it. And the ratio shows the ratio of the MPI reference divided by the HC MPI version. For these results in the HC MPI version, we only created one communication worker per node. So basically, there were 1,024 MPI processes for HC MPI, whereas there were 16,000 MPI processes for MPI. And you can see, and we also have, because we're using one core as a communication worker, you can see that we had, you know, in the two core case, or I should put a label of 1.0 over here, the performance of HC MPI was below MPI, but once you have enough cores, it more than dwarfs. In fact, there was some scalability issue that MPI was running into at 16,000 processes for this code. Okay, so I'm running short on time. I know we started a few minutes late, but I'm going to start wrapping up. It turns out that whole async await idea can also be directly executed in the distributed context. And in this sense, it's a little in the spirit of Charm++, in the sense that these data-driven futures can be just distributed across places and nodes. And the put get, the runtime takes care of communication for put get. If the producer and consumer on the same node, it's more efficient. If they're on different nodes, the runtime generates the communication. The difference, one key difference with Charm++, I'd say, is that these are very much part of the deterministic parallel constructs, the async await, whereas Charm++, oh yeah, and we get good results here in terms of scaling this on a more modest cluster, 96 nodes, 12 cores per node, and you can see improved performance both with increased number of cores and increased number of nodes. And with Charm++, that's more like what we view as our integration with the actor model. In the interest of time, I'm going to completely skip over the isolated stuff, which actually interacts a lot with transactional memory research, and we've done some work on comparing it, for example, with the Galois system, and instead of having a special runtime, just like Galois does, just use this unified runtime with isolated. So I think, being at Illinois, all of you must have also heard about actors. There's so many parallel programming models being worked on at Illinois. And one of the things we did was similar to HCMPI. We worked on integrating task parallelism with actors. Actors are a very elegant model, and Charm++ has these properties and others as well, where each char or actor executes its code sequentially. You don't have to worry about data races on the local state. But we wanted to add parallelism, and I don't have time to get into all the details, except to show you a simple example where we can do a finish, and this is again from my class, where you can start a bunch of actors and do a finish and wait for them to terminate, and that way you get a convenient hybridization, whereas sometimes termination can be very tricky in the actor model. Also, you have to have semantics for ordering of messages. In our case, we require that the order messages between the same sender actor and same receiver be preserved. Everything else, there's no constraint on the ordering. I'll skip this. They're also, you can think of these as asynchronous collectives, but the accumulator model, you can associate accumulators with the finish construct, where tasks can contribute values to accumulator, and at the end of the finish, you do a get, and you get the final value of the accumulator. And since finishes can be nested, these collectives can also be made hierarchical. So the role of the runtime system in all of this, I've really been trying to motivate some primitives, not really taking a stand on a particular programming model. I think different programming models can map onto these primitives in different ways. But I think the runtime actually has to play a key role in realizing these primitives and programming models. And a robust runtime can then bring about this composability, like I've been showing you, of course, improve performance, enable new programming models, also simplify the interfaces for system software, so it's kind of playing a mediating role. So this is where, so runtime can mean many things to many people. So for what I'm going to talk about right now, for the last couple of minutes, is really the bridge between the programming system, language, compiler, and what I'd call system software. Now, many people would call some of these part of runtime. But I think with the extreme scale systems, there's a need that many people working on software stacks have found, and I think there's a commonality coming on for this bridging. In the old days, you would let an MPI process make system calls directly, but that makes things brittle for a lot of the adaptation we want to do, or a lot of the malleability. So having this adapter actually, I think, is very key as we go in the future. And then both Bob and Sanjay referred to this open community runtime effort. That's something that a group of people working in the Extract project are discussing very much at an early stage. And the idea is to find components where where we can that can be made available as an open source testbed, so as to reduce duplication of infrastructure effort, but allowing different research groups to pursue their own research agendas. And so this is at a lower level than a programming model level. So something like async await would be mapped onto something like OCR EDT create with the whole parameter list related to dependencies, affinity, and all of that. And so the vision is and Bob had a slide related to this. You have an open community runtime framework, and it can be, maybe some people, more experts will program at those APIs, but otherwise you have higher level programming systems that map onto it, and we already have some examples. Definitely would like to explore, and we started some discussion with Sanjay about this on using OCR or using parts of Charm++ in OCR and getting more synergies there. There's also a foundation that's been created. The idea, if it succeeds, is to be, we have a narrower community in parallel computing, so create sort of the equivalent of Eclipse for this, for our community, and this is just starting out. So to conclude, I really think that you need a holistic redesign of the software stack to address these challenges, and you need execution models and integrate these hybrid dimensions of parallelism and heterogeneity. So I've tried to give another number of examples where constructs can be composed and interoperate with each other in beneficial ways. And I think the runtime actually is key to making all this work, because we can create all kinds of models that we like. And OCR is one starting point for a strawman community effort. Certainly, I would welcome talking to you guys during the break and the workshop as to what you see as the pros and cons of an OCR-like effort. We had a pretty active discussion of that at dinner yesterday too. So with that, I'll stop and welcome questions. Yeah. Okay. Yep. Yes. Question, Brian. Okay.
Not by value. So you actually have to make a copy of the object as it goes in.
So there is a global. So the question is, well, I think you may have got it, whether async await has call by value semantics. There are parameters that can be passed, and that's the convenience. And but there are the body of the async. For example, it could do a get on one of those objects in the global namespace, and that's still, so they can be okay, well, that's not a good example, because there we would have done the communication before async await. Depending on what you put it in the, let's see, what?
So my thinking is, say I have a big iteration space. I'm going to break it up into tasks. Right?
Yes.
But I'm doing the updates in place. So I can actually put the big chunk of data in, because I want the update to go back into that big array.
Yes.
And someone else has to know that you're done doing your part of the stencil. I can start working on my stencil.
Right.
So
the way we would do it is like the tile Smith-Waterman example. We would create a tile of these data-driven futures, and the await basically waits for the tiles.
It waits for the tile to finish, but not necessarily the data that's behind it. So
it would, if it actually reads the data, then if it needs to perform a get. So you can use the await in two ways. If you're doing some imperative programming under the covers on your own, you can just use the await as synchronization. If you're following more of the functional model, which actually can help you avoid data races, then you do a get of the tile inside the async await, in which case you'd get the communication also.
Yeah, I think unless you're doing...
a runtime person would think of it as it's a single assignment variable. Yeah. Yeah, I mean, the data-driven future is. And the backing data, it's up to the programmer as to, we did not want to dictate a functional programming model. A functional programming model would say everything is copy semantics, which you can certainly do, but we didn't want to require that. If you can just use it for synchronization and access shared state on your own. So for example, in our Degas project, we are looking at the global address space. We would just use this for synchronization, and then the body of the async could have PGAS access.
Yeah, talk to the PGAS. Yeah. Okay.
Okay, thank you. Yes.
The next talk of the day is probably a very broad talk as far as showing the utility of CHARMM++ is concerned. It's a group effort. Harshita led this effort in developing a series of mini apps in CHARMM++. And so this has been an ongoing effort. As you know, we had an HPC Challenge award 2 years ago that we shared with Cray at HPC Challenge competition at Supercomputing. We had another finalist, the 2012, and so some of these mini apps came from there. Some have been added new. Many have been updated and improved. And so Harshita will talk about those. And basically, the talk is titled CHARMM++ in Practice.
Thank you, Professor Kale. So as he mentioned, the title of the talk is Parallel Programming with Migratable Objects in CHARMM++ in Practice. So this is a group effort that has been going on for many past years. And some of the members whose work I'll be presenting today are mentioned here. So I'll talk about what are the main challenges that are faced by applications of today to efficiently scale to large number of processors. Then I'll go into the details of the RTS design that help alleviate some of these challenges, and what are the design decisions that went behind it and the features that get enabled due to those designs. Finally, we'll show that these CHARMM++ based design is capable of taking care of a wide range of mini applications. And these mini applications are usually representative of the full application. These mini applications have been implemented in CHARMM++. So what is the main challenge that is faced by applications to efficiently utilize the increasing powers, computational powers that are available today and also in the future machines? So one of the main challenge is handling the dynamic variations. So this dynamic variations can be due to application itself. So the application can be using certain algorithms which require irregular communication, or adaptive refinement which introduces load imbalance, etc., etc. The other case when the dynamic variations can be introduced is by the machine itself. There could be faults in the machine, or we want to constrain the temperature or power, or there is heterogeneity in the machine. So these are some kind of dynamic variations that are present. So how can an application still efficiently scale in the face of these kind of dynamic variations? So the runtime system are considered as a very essential component to handle these kind of dynamic variations. So, but just runtime system alone cannot do much, right? The programming model needs to support it based by providing it some of the design attributes. So we'll talk about some of the design attributes that are essential, but I'll just briefly talk about it because most of the people here know about it. So to efficiently, to empower the runtime system, the programming model needs to support over-decomposition, migratability, and asynchronous message-driven execution. The over-decomposition basically means decomposing the computation of an application into many more work and data units than the execution units. So the runtime system can manage the over-decomposed objects, map them onto processors depending on the load, communication pattern, etc., etc. So this is what is over-decomposition. Migratability is the ability to move work from one processor to another. So migratability along with over-decomposition enables many features such as like load balancing, fault tolerance, temperature, energy constraint, then malleable job scheduling, etc. I'll talk about some of these features in the following slide, but this is the general idea. Finally, asynchronous message-driven execution. So in a message-driven execution, And a work unit is being executed whenever a message is received for it, and not in a pre-programmed manner. So, and asynchrony means the sender need not block for any immediate receive from that receiver. So this is also very critical. This enables many things, such as, for example, if an application has to wait for a message, so there is some delay in the message, then there could be idle time. And this idle time affects the performance of the application. But while the work unit is waiting for a message to come, another work unit which is ready can be executed. So we are able to handle message latency by overlapping the computation with the communication. And another thing that comes out of this is you're able to spread the communication over time, and thereby reduce the pressure that is put on the network also. So Charm++ programming system uses all these attributes, and by using over-decomposition, migratability, asynchrony, we are able to get a very adaptive, introspective runtime system. So here are some of the features or capabilities of the runtime system that is enabled by the design. I'll talk about these in detail, but I've just mentioned the key ones here. There are many, many other ones too. So load imbalance is a very critical factor that affects the performance of an application. So for some applications, you can do a static load balancing, for example, like you do it at the very beginning and don't have to do it again. But for many class of applications with dynamic characteristics, the load imbalance varies during the execution, during the runtime of the application. So we need to perform dynamic load balancing. So over-decomposition with migratability enables load balancing. So the runtime system monitors the application, identifies load imbalance problems. Since there are many more objects mapped to processors, it can migrate the objects based on the communication pattern to reduce communication or want to balance the computation load. So Charm++ has a very rich, mature load balancing framework in it. We have many load balancing strategies as well that cover a wide range of things such as communication aware, computation centralized, hierarchical, distributed, and all sorts of load balancing framework. So the applications, depending on their need, can choose a load balancer to use. And it's very easy to use the load balancer also. So faults are becoming more prevalent as the system size scales. So it is becoming very critical that you don't want to restart the whole application when a fault occurs. You want to restart only from a certain point till the point that you have already executed. So the way it is done in Charm is with migratability, we are able to easily handle this. So the state of the application, it can be checkpoint to either disk or memory. And then when the runtime system notices that there is a fault based on the heartbeat mechanism, it can automatically restart these execution units on another PE based on the checkpoint. So, and Charm++ also provides four or so schemes for fault tolerance, which includes in-memory checkpoint, disk checkpoint, message logging, etc. Power and energy have become a big concern for the exascale machine, right? So one way to reduce the power would be to reduce the cooling energy, because studies have shown that a large part of the energy is used for the cooling energy. So how do we reduce cooling energy? We reduce the temperature of the room, but then reducing the temperature of the room can increase the chip temperatures. And we don't want the chips or cores to be overheating. So the way we have in Charm++ is the runtime system monitors the machine characteristics, machine temperature, and whenever it goes beyond a specified threshold, we use DVFS to control the temperature. But then just using, so DVFS basically means dynamic voltage and frequency scaling. So the cores which are having a higher temperature, their frequency is reduced, and the cores which haven't reached the threshold temperature, their frequency can be increased. But then doing DBFS this way can introduce load imbalance now in a tightly coupled application. So we also have framework and the runtime system that will monitor for load imbalance and trigger load balancing whenever it is required. So this way we are able to constrain the temperature and also minimize the timing penalty that is triggered due to the DBFS. So malleability is basically the ability to shrink or expand the number of processors that are assigned to a job. So why is this useful? This is because in clusters, this will help improve the utilization of the cluster and also reduce the average job response time. So with migratability, this can be easily achieved, right? Because the runtime system already takes care of mapping and remapping of objects to processors. So whenever we need to shrink a job, the runtime system will evacuate all the objects from the node that is being kicked out and migrate it to other processors. And when we are expanding, the objects can be migrated from other PEs to the newly assigned node. Next one is communication optimization using TRAM. In some applications, when there is a large number of fine-grained messages, the overhead of the fine-grained messages can constitute a large portion of the total application time. So we use TRAM, which is topological routing and aggregation module, to aggregate these fine-grained messages into large message and route it. With all these complexity and dynamic variations, runtime systems are becoming very popular in handling these kind of variations and taking care of the performance of the application. So the key idea is we don't want to put too much burden on the programmer to monitor all these variations and change the application accordingly. So in CHARM, we have an introspective runtime system module called control system, which basically collects certain characteristics of the application in the machine, monitors them frequently, and then analyzes it to figure out what are the changes that are required. So the application interacts with this control system based on control points. These are basically parameters that can be tweaked. So the control system, after monitoring the application, will decide which control points to tweak and how to adjust them. And it can reconfigure the application to improve the performance, basically. Interoperation. So what is interoperability? The motivation came from the fact that many applications require modules that are best fit for certain kind of parallel programming paradigms. So to obtain the best productivity and performance, we want the programmer to write these modules in the language that is most suitable for it. So interoperability is basically enabling these modules, which are written in different languages, to interoperate, to execute it in the same application. So in CHARM, we have implemented interoperability between MPI and CHARM++ module. We also experimented the practical utility of this interoperability using CHARM, which is not CHARM++, which is a cosmology code written in MPI, and we find that that's a scalability plot of that application. We find that towards larger number of cores, about more than 20% of the time was taken up by sorting algorithm, histogram sorting algorithm. So, and CHARM was providing a highly parallel scalable histogram sorting algorithm. So when we replaced the sorting algorithm in the native code with the CHARM++ library, the performance of it improved significantly, and the total execution time for the sorting from 23% came down to just 2%. So this is one of the examples where interoperability, one way or the other, CHARM++ module in an MPI application or an MPI module in CHARM++ application can significantly improve the performance of an app. application. Now I'll go into the details of mini applications that are written in Charm. These mini apps are representative of full application in that they capture the communication pattern and certain computation kernel of the full application. Most of these mini apps have dynamic characteristics in them in that they have load imbalance or adaptive refinement or something like that. And we show that these features and the design model that we talked about is applicable to a wide range of mini apps. So here's the adaptive mesh refinement mini app. So adaptive mesh refinement is widely used for obtaining numerical solutions for partial differential equations. So if we have a simulation which uses AMR, but the certain regions of the mesh which requires higher resolution are being refined while keeping the other regions of the mesh at a coarser refinement level. And we can see that in the simulation that is shown here. So in the AMR 3D is a mini application that is written in Charm++. So if we use a process-based decomposition, many of the blocks are assigned to one process, and the programmer has to explicitly take care of managing all these blocks, taking care of its communication, refinement levels, etc., because these blocks can be at various different refinement levels. If we look at the object-based decomposition model, which is used in Charm, every block becomes a char element, and they are independent and they are migratable. So this makes it very easy for the programmer to code, maintain, and debug the whole process. So during refinement process, new blocks are being created, which is taken care of by dynamic insertion of char array elements in Charm. And during coarsening, these blocks are being deleted, which is also happening in a dynamic fashion. The runtime takes care of all those dynamic insertion, deletion, and all the things that come with it. Also, this dynamic refinement and coarsening introduces quite a lot of load imbalance. And that was one of the significant factor that was hampering the performance of this application. So since Charm has a wide range of load balances, we could try the different load balancing strategy. But the one that we use for this is a highly scalable distributed load balancer, which uses partial information about the global state of the system to efficiently load balance this application with very minimal overhead. So here we see the strong scaling result of AMR 3D. This was run on BlueGeneQ 128K cores. X-axis is the number of cores and y-axis is the time per step. We see that we are able to achieve good scalability till 128K cores with about 46 to 50% efficiency. And the distributed load balancer is able to obtain about 40% benefit at 128K cores. Here over decomposition also helps quite a bit, because when certain blocks are waiting for some messages to arrive, the other blocks can overlap it. And that overall helps improving the performance of the application. We also have tried the fault tolerance protocol in AMR. We used in-memory checkpoint for this purpose. This is a plot that shows as we increase the number of cores, what is the checkpoint and restart time. You can see that the checkpoint restart time decreases with increase in number of cores. This is a strong scaling result. So the amount of checkpoint that each core has to do also decreases with increase in number of cores, which is why these time decreases. And at 32K cores, the checkpoint time is only 29 milliseconds, and restart time is only 470. Yeah. How many total cells? Akhil, do you remember how many total cells were there in this AMR application? Yeah.
What is the size of the block?
Yeah. Nine is what I used for this. This is in memory checkpoint, so the time takes, yeah. Right. Sure. So during restart, when we have any faults that occur in between during restart, you have to obtain the checkpoints that are stored in your buddy processor and put it in another processor and restart from that last checkpoint. That is the time. The fault is detected based on the heartbeat mechanism. So the next mini application I'll talk about is molecular dynamics, which is also LeanMD. This basically calculates the forces on the atoms based on Lennard-Jones potential. So here is a domain decomposition of the molecular dynamics simulation. So basically, the 3D domain consists of atoms, which is over decomposed into cells, which is a char array, and the computes, which is also a 6D char array. It is sparse, and it performs a pairwise force calculation between the cells. So the computes can be of totally different number than the cells, and they are mapped by the runtime system onto the processors. Here we show the strong scaling results of LeanMD. We use a 2.8 million atom system. We ran it till 32K cores on BlueGeneQ. So the one characteristics of LeanMD is that it has gradual load imbalance, and not any drastic load imbalance that we saw in AMR. So the runtime system monitors the application, and whenever significant load imbalance is triggered, when significant load imbalance is noticed, it triggers load balancing. And load balancing is triggered when it is also profitable, because you don't want to do load balancing very frequently, where the overhead is much more than the benefit that you get. And we use a very scalable load balancing strategy here, which is a hierarchical load balancing strategy. It's able to improve the performance of the application overall using this. Again, we show the fault tolerance protocol in this. We use in-memory checkpoint restart with simulated failures. We show it till 32K cores of BGQ. Again, at the large scale 32K cores, the checkpoint time is only 33 milliseconds. The time taken to checkpoint its data onto the memory, and the restart time when the failure occurs is 139 milliseconds only. BANSAT is a tree-based n-body simulation code. So here the three-dimensional space consisting of particles is decomposed into tree pieces. So the goal of this BANSAT mini app is to calculate the forces on these n particles based on gravity. So at each time step, you calculate the forces on these particles and also move these particles based on the force calculation. So here we have a three-dimensional, let's imagine a three-dimensional space with the particles all around. We use different domain decomposition to decompose this domain into tree pieces. Each tree piece, which is a char array element, is responsible for certain regions of the space, a certain particles in this region, and it calculates the forces on them and takes care of moving the particles also. So there are two kinds of work that comes into play during force calculation. One is the local work, which is calculating the force based on other particles in your own treepiece. And the other one is the remote work, which is for which you need to communicate with other treepieces to obtain the particles information and then do the force calculation. So we use prioritized messaging for this. So the remote work is given higher priority because once it starts, it will start sending the messages. And while we are waiting for the messages to come back, we start the local work, which is a lower priority. And this overlaps quite a lot of delay in message and helps improve the performance. We also use a specialized load balancing strategy for this. So this is using ORB. ORB is orthogonal recursive bisection. So this takes care of some amount of load imbalance as well as the communication pattern while assigning the treepieces to processors. This is the strong scaling result of BANSET for 500 million particle system. And we ran it on 16K cores on Blue Waters. So we find that over decomposition and load balancing improves the performance of BANSET with respect to no over decomposition and load balancing. No, so we try to balance the number of particles in each char almost, keep it almost same, but there is a threshold within which we do it. Yes, so we do in a time step we have domain decomposition which distributes the particles amongst chars, and then we do force calculation and migrate particles. Then the next time step again does domain decomposition. So it's a yeah, the tree has to be reconstructed during every time step. Yes. No, that is a very small portion of the actual force calculation. And in the next talk that Tom's giving, we have Changa, which is an application based on which BANSET was written, and we'll show some of the numbers and high scalability that we achieved on 500,000 cores. Yeah, but it's only a small fraction of the total force calculation. Next, we also implemented PDIS mini application using YONS protocol, which is a windowed conservative protocol. So we have a char array, and each logical process is a char array element, which takes care of executing the events, basically. So there are two steps to it. First step is identifying the window in which these events can be executed, and the second stage is actually executing the events. So in the first stage, every logical process, LP, informs what is the earliest time in which an event can be sent. And that is the window in which, that's the earliest time that a new event can be generated. So you find a window in which all the events can be executed without being preempted, and all the logical processes start executing the events. So in this mini app, one key thing is that you don't really know a priori what is the communication pattern. So using an asynchronous message-driven mechanism, you can, whenever a logical process receives a message, it starts executing it. So this reduces the complexity that goes into implementing this kind of mini app. And we also noticed that the key characteristics of PDIS is that it has large number of fine-grained messages, and we use TRAM to optimize this, and we obtain good performance with TRAM. Basically, what TRAM does is aggregate all these fine-grained messages into a large message, thereby reducing the overhead of all these tiny fine-grained messages. So here is the benchmark, the scaling plot of the benchmark, performance plot of this benchmark shown. On the left-hand side is the simulation events per second that we obtain with increasing the number of cores. And we tried for different number of over-decomposed LPs per core. So with 64, 128, and 256. We find that as we increase the number of objects per core. That is, as we increase the over decomposition, we are able to obtain better events per second. So over decomposition helps quite a lot in improving the performance. Basically, because if one LP is waiting for, doesn't have any events to execute, another LP on the same P can start executing. And on the other hand, other side is the improvement that we obtain from TRAM. That so TRAM is able to improve the performance over the base case quite a lot. And in the 1024 events per LP, we're not even able to run the app, mini app without using TRAM. So it improves significantly. So all these design design attributes we talked about, over decomposition, migratability, and asynchronous message driven, we can use it in MPI applications also, using an AMPI framework that is in CHARM++. So we can port the MPI application that is written into CHARM++, and then it can use all the CHARM++ features that come with it. So one key thing, so I'll talk about what is Lulesh. Lulesh is a mini app from Livermore, and we found that over decomposition of this mini app basically improves improves the performance by overlapping the communication with computation, and also by over decomposing, you are making the domain size smaller, which will fit into the cache now and improve the cache benefit as well. We also noticed that there is a small amount of load imbalance in Lulesh, which can be mitigated by load balancing strategies in CHARM++. The migratability can be easily enabled in AMPI application using IsoMalloc framework that's there. It's automatically enabled, and all you have to do is just call the appropriate load balancer, and load balancing is taken care of automatically. The last point that I want to make here is, since we have over decomposed the domain, we can use any number of cores to execute this, which is not the case in usually in the MPI process. They have to be cubic number of cores. So here is the weak scaling plot of this. On y-axis is the runtime, and x-axis is the number of cores. We find that AMPI version with over decomposition, yeah, Lulesh 2.0, which, yeah. I find that the AMPI version with over decomposition performs significantly better than AMPI version without over decomposition and the MPI version. It's almost 2.4 times. The speed up is almost 2.4 times. Also, the small amount of load imbalance that is there in the Lulesh 2.0 benchmark, we're able to handle that with the load balancer that we use. One more thing to notice here is the 3000 and the 6000 6,000 processors that are here. Those are not cubic numbers, and we can the AMPI version runs for them too. So it doesn't have to be necessarily a cubic number of processors to run this application. So in summary, we have shown that the many applications can benefit from the CHARM++ design model and the features that get enabled due to this design model. And we are able to improve the performance and productivity of these mini applications. These mini applications are representative of the full application. And if you guys want to read more about the work that has been there, all the papers are there in ppl.cs.illinois/papers. That's all. Thank you. Thanks.
We'll start at 10:45. So this game for
You had the last one?
Pretty sure, yeah. Zero thinks it's there, but
Well, yeah, I need to change.
oh, yeah.
The only problem which I've seen so far is that the PPT expression that itself would happen. Right. Oh, you have yes, PowerPoint.
Oh, yeah, that's right.
Yeah, this is, yeah. I think this gets back to the potential for
It's something else. Like, my
okay. Oh, I see. Yeah. No, yeah. So is oh, yes. Yeah, like through the year. Easier. Well, in the week of transfer to data. Yeah, 90%.
Yeah, I don't know about
Yeah, yeah. It's software perspective. Yeah, so we'll have to do, we'll have to have. Really fast, collective. Oh, yeah, I was trying to see that. Okay, yeah, you can see it. You can see it. Oh, okay, you can see it. Okay. Oh, you can see it. I guess they had to go. Let's do it. Whatever you gotta fix them in one way, we gotta reach yeah. They run it. Sure. I mean, there's other. Yeah. I guess. Yeah.
Hello everyone, my name is Abhinav. I'm also a former PPLer and it's good to be back. So this session is about applications and the first talk is by Professor Tom Quinn from University of Washington, Seattle. And this is one of the coolest collaborations we have. You'll see Tom usually has nice videos of cosmology simulations, so pay attention.
Is it on? Yes, okay. Right, so I'll be talking to you about this cosmology code, Changa. Oh, yeah, thank you. Go ahead. So you can see, this has been a collaboration that's gone on for a while, so we've got a cast of thousands, both from the PPL here and people that have been in my group at the University of Washington. We call our group the M-Body Shop because we do M-Body simulations of a number of different astrophysical phenomena. The collaboration was started with funding from the NSF ITR program, and we additionally got funding from NASA. So today we'll start off by giving you a little overview of computational cosmology. We recently got a large allocation on blue waters, so I'm going to explain the scientific motivation for that particular allocation and running Chang'e on blue waters. Then I'll go into some of the Chang'e design, which is very similar to that Barnes Hut mini app that Harshita talked about, and some recent results both in terms of scaling and science publications before, and by talking about future work. So let me start out with the quick history of the universe. Okay, so obligatory plot. So on the horizontal axis is the age of the universe in a logarithmic scale, highly logarithmic scale. And then there's a very distorted distance scale on the vertical axis, attempting to show how the universe expands over time. A couple remarkable things. By observing the cosmic microwave background, we actually have direct observation of the universe when it was only 380,000 years old. What's even more remarkable is that the temperature fluctuations that we see in the cosmic microwave background appear to be an imprint that started as quantum fluctuations when the universe was less than 10 to the 32nd seconds old. And furthermore, I put up this particular slide because recent results from the BICEP collaboration have made observations of the polarization of the cosmic microwave background that have put observational constraints on the physics of the rapid inflation of the universe that is happening at this very early time scales. I think this is amazing that we have direct observational constraints on physics at the 10 to the minus 32 seconds in our universe. So that's remarkable. The other thing that's going on, of course, is that these density fluctuations eventually turn into the stars and galaxies we see today. So again, the large-scale structure in galaxies also reflects the quantum fluctuations at the very start of the universe. So, for example, this is from the Sloan Digital Sky Survey. It's a distribution of galaxies, and you see these voids. The size of those voids directly maps onto the size of the density temperature fluctuations we see in the cosmic microwave background. Again, going back to the very earliest times in the universe. Now, an issue with this particular picture is that we're not really seeing the underlying mass of the universe. These points here are galaxies, and if you zoom into one of those galaxies, it looks like this, and you're seeing a lot of very complicated physics going on. The light you see is generated by stars. It interacts with surrounding gas. It gets absorbed by dust, which are the dark spots here. It gets reflected off of other bits of dust. And so there's a lot of hydrodynamics and baryon physics that goes on in order to understand how those density fluctuations turn into this kind of picture. And we want to understand that collapse and that interaction because we hope to get some more clues about what the contents of the universe are. So that picture I just showed you is just a small fraction of the total energy density content of the universe. And so we're trying to use what we can see from the light to infer this mysterious stuff that we call the dark matter, which corresponds to about a quarter of the energy density universe, and this even more mysterious stuff that we call dark energy, which is the bulk of the energy content of the universe. And previous simulations have put constraints on what this dark matter is. For example, it can't be ordinary neutrinos. It needs to be something either more massive or more exotic, and I have a couple of candidates here. So in terms of computational cosmology, what we're trying to do is we're trying to take those fluctuations we see in the cosmic microwave background, which are 10 to the minus 1 part in 10 to the 5, and under the gravitational collapse, self-gravitational collapse, we create these galaxies. The centers of those galaxies are over 1 billion times more dense than the average density of the universe. And we want to follow that with enough fidelity to make these testable predictions. And so we need this highly nonlinear dynamic calculation. And just to give you a pictorial sense of the size scale we're talking about. So here's moderate scale structure. This isn't actually the largest scale structure in the universe. You see filaments and voids here. We zoom into the intersection of one of those filaments, and we've got a roughly round dark matter halo. We zoom in by another factor of 10, is the disk of stars and gas, which is the thing that we actually observe. And just to make the point that, well, first this point, there is essentially a fractal-like structure to the dark matter as we zoom into smaller and smaller scales, as shown in this particular simulation. And so that presents this computational challenge of covering many orders of magnitude in spatial dynamic range, cube that number to get the dynamic range in mass, but that spatial dynamic range also implies a large temporal dynamic range. The time scale for star formation, for example, is less than 1 million years, and we have to follow that for the age of the universe. And so that means that we can't be updating the entire large-scale structure of the universe at these tiny time scales. And this is further made a challenge because gravity is a long-range force. For example, the spin of our galaxy comes from forces from the nearby cosmic structure, which spans many tens of megaparsecs. And so you need to follow this information across your entire computational domain. And just making the point that we want to make predictions about this. If we had dark matter goggles, this is the structure we would see in the dark matter. You see these things are quite different. That's because the baryons obey the laws of hydrodynamics as well as just self-gravity, which controls what the dark matter is doing. How do you get the... So this is, all right, so this is a prediction from what the, this is theoretical model of what a particular type of dark matter would produce, okay? And so we have to say, well, does this create one of these if we put in the baryonic physics? Essentially, right. I mean, there is also hope that we might be able to detect this dark matter in, say, annihilation signals. You may have heard some announcements about seeing gamma rays from the center of our Milky Way, which may be an indication of the dark matter, a direct indication of the dark matter. Aha. Exactly. Yeah. Yeah. So yeah, technically the term is the dark matter is collisionless. It can pass through each other. It's very tiny cross section. Ordinary matter, on the other hand, shocks and is subject to viscous hydrodynamic forces. So as well as calculating gravity, we need a method to calculate those hydrodynamic forces. We use this technique called smooth particle hydrodynamics. It's a method that works well when you have high Mach number and large density contrast. That's partly because it has this Galilean invariance. So if you have bulk motion, it does not change the equations of motion. It's also this Lagrangian method, so it actually follows the flow as you go into large density contrast. And the way to think of this is a Monte Carlo method for solving the Navier-Stokes equation. And the other thing is because it's made of particles, it makes a natural extension of the embodied techniques that we use for calculating gravity. So we use the same data structures to calculate the hydrodynamic forces as we do to calculate gravity. We do have to worry about star formation. Where do the stars form? This is physics that happens on the sub-parsec scale. So if we're to directly model this physics within cosmology, we're probably talking about Yada scale computing. So we already heard zeta, so I had to go one beyond. Talk about Yada scale. But so we don't have that yet. So what we're doing, we have a subgrid model where we resolve things on scales of hundreds of parsecs, and if it's above a certain density threshold, then we have a scheme for turning that gas into stars. Stars go supernova, and so the energy from those supernova also affect the gas. They also do interesting things like inject metals. By metals, I mean carbon, oxygen. Sorry for the chemists, but this is what astronomers call metals. Yeah, hydrogen and helium are not metals. You know, chlorine, that's a metal. Neon, that's a metal. Okay. But the importance is that's the stuff you and I are made of. Okay. And so understanding this feedback is also important. And so we have this as a subgrid model in our simulation. We have been doing these kinds of simulations for a while and have been able to reproduce things that look like galaxies, starting from the cosmic microwave background fluctuations, both in terms of making disk-like things, getting the radial density profile right. So we think we understand how we can model galaxies. This is one galaxy. Here's the Hubble Space Telescope view of galaxies. This is a field for which many, many hours of the Hubble Space Telescope was used to get an idea of the population of galaxies in the early universe. So this is a snapshot of when the universe was only a tenth its current age, and we see various types of all these little smudges are not stars. Each little smudge is roughly 1 billion stars in this picture. And we'd like to understand, why are these things red and these things blue? Why are these things disc-shaped? So understand the entire population. And so to do that, we need to model a whole piece of the universe with sufficient resolution to get that morphology. And this is the goal of the allocation we have on Blue Waters, is to understand these kinds of questions over an entire population of galaxies. And just so if you look at the largest scales, well, I wouldn't say largest, but large scales, the evolution proceeds like this. It loads. There we are. You start with the small density fluctuations. Things collapse under their own self-gravity. The collapse evacuates voids. The material from the voids tends to collapse into the filaments. As the filaments intersect, you get larger galaxies forming. If you have really good eyes, you'll see that these galaxies are forming stars, and there are supernovae going off that you'll see occasionally gas being expelled from the galaxies. But this is kind of the largest scale. We want to make sure that we understand the morphology of each of those galaxies that we form, because that's what we're going to compare with the Hubble Space Telescope observations. So here's a simulation that we just finished. It's also a simulation that the group here has been using for scaling tests. Here's it's a 25 megaparsec section of the universe. We zoom in again, we zoom in again, and we can resolve an individual disk of a galaxy. There are hundreds of these kind of galaxies in this box, and so what you should be thinking of when you looked at that at the last movie is that for each of those galaxies in that last visualization, we have this kind of dynamics going on, right? The galaxy is not this smooth buildup of material. It's actually a merging hierarchy of smaller lumps into larger lumps, and the dynamics of that merger, of those mergers, can be quite, well, interesting. As objects come in, you'll see that they incur a burst of star formation. For example, here's a little guy coming in. All right, first of all, it sort of disintegrates. The dark matter halo is still there, so as it goes by, notice there's a burst. All right, that's a star formation that's feeding back onto the gas. You notice as this guy went by, another burst happened, and of course, eventually this whole thing merges together with a very strong burst of star formation. This all affects the morphology and how the galaxy looks to us as we observe it with the Hubble Space Telescope. So question. Sorry, just get the scale. So that's the size of the box that we're looking at. All right, so this is a box that's 50,000 light years across. That's roughly the size of an individual galaxy, right? And we have hundreds of these things within this 80 mega light year volume. And the conversion from light years to megaparsecs is roughly a factor of 3.
How do you make those models and matches the Hubble telescope observation?
Well, all right, so there's two things. One is sort of verification, right, that we are following the laws of physics we think we're following. And, right, you run the standard tests. We're actually part of this collaboration of roughly 100 people where we're comparing different cosmological codes to make sure that we're getting the same results. So reproducibility is a big part of making sure that we're doing the right thing. And so as part of this collaboration, we're also comparing the star formation and the hydrodynamic physics that we put into these simulations. So running the standard test problems, comparing with other codes is sort of that verification process. And then part of the prediction is, all right, do we make galaxies that look like what we observe? If we don't, then we've got some, we got some science going on. What's wrong with our model? In this one, it happens to be yes, because most of the universe is dark matter. So it's roughly 4 to 1 or 3 to 1, something like that, gas to dark matter in this particular simulation. Well, I'll talk a little bit more about that because, yeah, no, a very good point. In this particular simulation, we have a density threshold. If the gas is above a certain threshold, it forms stars on a dynamical time, and we've got parameters to adjust that. Basically, we're trying to match observed sort of density to star formation rates ratios that we see in nearby galaxies. Also coming up, yeah. Periodic, right? We're trying to model an infinite universe. Kind of hard to fit in a computer. The inflation, so the overall expansion of the universe is modeled. Okay. Yeah, the size of the box expands with the universe. Yeah. Yeah, basically we follow the equations for the expansion of the universe. All right, so that's what we're doing today. What we plan to do is to go down by an order of magnitude. So 2 billion today. Hopefully by this summer we'll start running a 25 billion particle simulation. And of course, with the corresponding growth in the size of our data sets, you asked about black hole feedback. That'll be the new inclusion, and also molecule formation, because we know that star formation is correlated to where the molecular gas is, and so that's to be is being incorporated as we speak. Just preliminary results here. This is a luminosity, star formation rate as a function of what we call redshift. These are early times, late times, observations, this recent simulation. The fact that our simulation falls above observations is not too much of a worry because the telescope can't see every star, whereas in our simulation we can. So if it fell below, we'd be in trouble, but this is okay. We make this interesting prediction. The gray area is what we can observe, and we make this prediction that there's actually a rise in the star formation rate at very early times in the universe. We'll see if that bears out. So we've been doing all this with a code called Chang'e. It's got a lot of features for cosmology, production code. I want to talk a little bit about its structure. Latency hiding is gravity causes a lot of communication, so hiding that communication latency is important. You've heard about over-decomposition. We do that by putting pieces of the tree, many more pieces than we have cores. But even within a char, we divide it into multiple work units, even dividing the off-processor gravity with the against the on-processor gravity, and the hydrodynamics, and the periodic boundary condition calculation. We also, Harshita talked about this, methods that cause data requests are executed first so that those data can be gotten for future execution. Structurally within a processor, we've got many chars, and here's the division between local and global. Of course, the data that these things require tends to be the same, and so we avoid data duplication with a software cache, so that if one tree piece needs some data, it's stored locally so that if a second tree piece needs it, it doesn't have to go for a second communication request. And here's how the calculation proceeds over time. So this is time and utilization of the machine. The gravity bits are in blue, shades of blue, with remote work, local work, and periodic work. And then the hydrodynamics are in green, with this is essentially the continuity equation, the momentum equation, and the energy equation. All right, ooh, okay, we got to finish soon. Somebody's, sorry, okay, yeah, I got to finish it.
I'm going to ask a question, why do we have that big, I don't know, but why do we have that
right here? All right, so in order for the pressure to be calculated, you need to know the density. So all the densities have been found, you can calculate the momentum equation. I've got to move along really quickly. Scaling to 500,000 cores with 12 or 24 billion particles is our recent scaling results. This has been due to work by Harshitha and Lukash, working on eliminating a lot of the fixed costs. And this was talked about a little bit during the last slide. Just point out some timings here. Without some of these optimizations, the domain decomposition and the tree build and the load balance in particular were taking a lot of time. After we've optimized it, in particular moved to a hierarchical load balancer, the fraction of time taken by the load balancing drops significantly, and that's allowed us to scale to 500,000 cores here. Seconds. And just a summary, these sort of fixed costs were important. That was for a uniform volume. I mentioned that gravity causes this large load imbalance, both because of the time stepping and the force calculation. This is not particle distribution, this is the distribution of the chars in space, colored by the load that each char has. And see, if you're in the center of a cluster, you've got a lot more work to do. The ORB domain decomposition that Harshitha talked about makes it look like this. Now the coloring is by processor number. Okay, and so you can see how the ORB tries to split things up, keeping things spatially local. However, you still have significant load imbalance because of the multi-stepping. So instead of having a nice even distribution of load around 1, we have the vast majority of the pieces in the small time step have 0 load, and you've got only a few hundred pieces to distribute. So that's a huge load imbalance. One of the things we've done to correct that is some intranode load balancing. So here's one of those heavy pieces. We've got a bunch of empty cores on a node, and so we just essentially do work stealing for that piece. Communication imbalance is another problem. This idle time here is because a lot of pieces are busy satisfying data requests. And so what we've done is duplicate those pieces so that we spread out the communication load, and now the time profile looks like this. So for these cluster runs, which are multi-stepping, only going to 130,000 cores here, but we're still getting a good fraction of parallel efficiency. If we also include the multiple time stepping, the fact that we're only evaluating forces occasionally for the slow-moving particles, we don't get as great a parallel efficiency, but you notice that the actual time can go down by a factor of 4. So in terms of utilization of the computer, we're not as great, but actually time to completion increases significantly. Okay, that's the scaling results, some science results. Here's a paper from last year where we're looking at the microwave signature of clusters. Here's a paper that I'm not an author on. It's a Nature paper that uses Chang'e to model the interaction of a dwarf galaxy with our own Milky Way. And the point of the paper is that this collision that happened a few million years ago is responsible for some of the spiral structure we see in the Milky Way. Just to point out, the code is being used by others as well as our own group. And I already talked about this. We're going to be adding black holes, and we need radiative transfer to find out where the molecules are. We're experimenting with different forms of dark matter, but there's also the algorithmic improvements as well. And yeah, well, let me finish here saying, right, this has gone on for several years now, but we've been successfully addressing these computational challenges using many of the features of the CHARM++ runtime system.
Thanks, Tom, for the entertaining talk.
Do you have a sense for by how much the fidelity of these calculations would be improved by adding more particles? Well, you're already at 2 billion, right? But if you say went up by a factor of 10, from a physics point of view, how much would that improve the simulation?
So the reason we're going from 2 to 24 is exactly to improve the physics. That is, in order to understand the morphology of a given galaxy, we need of order 100,000 to 1 million particles in an individual galaxy halo. So as in this particular kind of simulation, as you increase the particle numbers, you can see smaller and smaller galaxies. So that's how the fidelity will improve. Correctly model smaller and smaller galaxies.
Question.
So you have multi-step and not multi-step, I guess. You have different modes you can run the code in.
Yeah.
So in the multi-step, you're subcycling the finer nodes of your Chang'e tree at a finer time scale.
Right.
But you still need a globally consistent gravity background field.
Yes.
So you're solving the global gravity field at every single fine time step?
That's correct.
All right. How do you handle the mass being deposited on, as the course grid advanced in time and then you time interpolate?
Yes, so we rebuild the gravity tree every small time step.
Okay.
Fortunately, that tree build is only less than 10% of the calculation, so it'd be nice if we could do some tree repair or something like that, but that's a little more sophisticated algorithm.
But your coarse cells still are, your coarse particles are still moving at a slower speed. I mean,
that's right.
Your background mass is shifting during your fine steps. So
that's correct.
Do you time interpolate? Do you extrapolate those mass positions to get it more
time interpolate.
You time interpolate it.
Yeah.
All right. So they leap forward in time. Then you do a correction for them after.
Yeah.
All right.
Let's thank Tom once again.
So while you're doing this, multiple month-time stepping was going to be quite a bit of we can make a story of
So the next speaker is Jason Yum from Virginia Tech. This is a relatively new collaboration compared to the older ones, and this is on epidemic simulations on large machines.
Okay. So today I'm going to talk about epidemics, contagion simulation software that we implemented in CHARM++. And this is a joint collaboration between PPL, Lawrence Livermore, and Virginia Tech. So I'm going to go over the epidemics briefly. and talk about what kind of scalability challenge that we have faced when we try to run this code on large-scale platforms and how we overcame them. And then finally, I'll present the performance results. So Epistemdemics is an agent-based simulator. An agent represents a person in the social network, and the interaction between people are computed by the other types of object called locations. And we represent social network as a bipartite graph like this. There are two different types of vertices, and the edge connects the vertices from different types. And a diffusion event may lead to interaction may lead to a diffusion event, and such as the disease infection. And an agent has its own state machine, independent state machine called PTTS, probabilistic time transition system. And in PTTS, a transition can happen spontaneously, such as recovering from disease after a random period of time. Also, it can happen by an external trigger, such as disease infection. So this is basically what Epistemdemics do. And the key input of the Epistemdemics includes a population data set. And for this study, we use a population data set, different size and geographic locations represented. And these data sets are generated based on sources available to public to match the demographic distribution of the real population of the United States. So in Epistemdemics, each iteration represents the day of the social network. So in a day, there are two computation phases followed by a reduction phase. So at the first computation phase, each person computes its health state and then also determine which locations to visit during the day. And then while doing so, it sends out visit messages to the locations to visit. And at the end of the phase, there's a global synchronization to make sure the delivery of all the messages. So this is necessary because there's no a priori information of the source or the number of messages to expect. And then in the second phase, locations compute interactions between visitors. And while doing so, it sends out, if there's an infection event, it sends out the infection notification message to the person who got infected. And then there's a global update of simulation scenario variable. So we distribute person data. So we have two different types of char arrays here, person manager char array and location manager char array. And we distribute person object across these char array elements and location object across these location manager elements. So that's how we use charm underneath. And there are features that we use from the charm. So we use either CD or QD for the synchronization, and we rely on TRAN for handling a large number of small messages. And we also take advantage of the SMP, and we also speed up the data loading using the latest interoperation for MPI-IO. And we use a projection to diagnose the performance problems. So with Epistemdemics, both the strong scalability and weak scalabilities are important. For example, a few years ago, when there was a avian flu pandemic going on, the health scientists and government policymakers required the simulation results for various scenarios every morning. So that's what motivated this. And then also, we currently have population data synthesized for the entire United States, and we plan to extend this to the global scale in the future. So we use large-scale platforms such as Bluewaters and Vulkan, and that's when. So when we first started to run our code on these platforms, we noticed some unexpected scalability problems, and that's the main focus of this talk. So just to get a sense of what how the code behaves. So in epistemics, we have large portions of data accesses and branching, and very small portion of floating point computation. So there are 58.3% of L1 cache, data cache accesses, and 19.3% of branching, and 70% of those branches are conditionals. And the yellow bar here shows the miss ratio of the conditional branch, and this green bar here shows the L2 data cache miss ratio. And we talked about the phase of computation in the algorithm. So this blue represents the portion of the time spent in person computation phase, and the orange represent that of the location computation phase. So when you first try to run this code on large-scale platforms such as Blue Waters, the strong scaling behavior was not satisfactory, so it stopped scaling at 1K cores. So our first optimization effort focused on reducing data accesses and branching. As a result, we got significant improvement in weak scaling. The execution time was reduced by at least 40%, and the memory footprint was reduced by 50%. And the plot on the left side shows that in terms of the ratio of the hardware counter before and after optimization. So for example, in this case, the L1 cache access ratio is less than 0.8. That means that it is reduced by at least 20%. But the strong scaling didn't really improve. It hasn't improved much. So we further took advantage of the SMP mode in Charm++, and that made us go a little further, but it was apparent that we were hitting another bottleneck. So that's what we are going to talk about. And those bottlenecks were actually from the data itself, not from the code or the runtime. So there was extreme variance in the load of work, originating from the heavy-tailed property of our data. And there is trade-off between data locality and load balance. So if you want to optimize one thing, then you may have to sacrifice the other thing. And epistemics also generates large amount of fine-grained messages. So for example, you can generate as large as 1.5 billion messages, less than 40 bytes each per iteration. And there's uneven amount of communication among processors. So to optimize the locality, in other words, to minimize non-local accesses in processing graph data, we rely on graph partitioners. And because graph partitioners allow us to specify application-specific load balancing constraints via the vertex weight in optimizing locality. So for that, we developed load estimation model like this, based on function approximation approach. So the target of the model is the load, what we call load, and it's a relative processing time of location vertex. So, and the input to the model is the application variable, such as number of events. So each visit to a location creates 2 events, an arrival event and a departure event. And edge from a person to a location represent a unique visitor, and a visitor may visit the same location multiple times. So we do this by using piecewise linear regression, and we observe the average error from 5 to 7% across the platforms that we tried. And we only use the statically available information to do this. And in the future, we would like to include the dynamically available information to handle dynamic load variation due to the scenario changes of the simulation. So when we applied this load model to graph partitioner, the the estimated speed up for each data set was like, it was bounded. So it didn't go beyond a certain point. So this estimated speed up is computed here as the total load divided by the maximum of total load per partition. So to get further insight on what's going on there, so we conducted an analysis based on some simplifying assumptions as this. So we assume the degree in the graph follows a power law distribution. For example, in other words, the number of vertices with the d edges are proportional. It's proportional to the exponential term of d with the negative exponent. And we assume that the complexity of work at the location vertex is order of degree. And then, so we further assume that the vertex load is the degree times some constant. So the goal here is to find out the maximum, the upper bound of the speed up. So we compute that by dividing the total load in the data set by the maximum load over vertex. So we can do that by summing the load of all vertices, and then that we can compute by alpha times size of the data times the average degree. And the maximum load is with the maximum degree from the vertex at the load model. So by substituting these two terms here, we get the relation at the bottom. Now, to compute this log of Dmax, we have further assumption from the power law degree distribution that there is only one vertex with the maximum degree with given the size of data d. From that, we can we get this relation and we substitute log of Dmax, and we finally get the upper bound scaled by the upper bound of the speed up scaled by the size of the data as this formula. So we know that the beta and C and D are all constant, but we don't know whether the average is constant or not. So we compute the D average as the expected value of the degree, and the degree ranges from 1 to the total number of vertex in the data minus 1. So the denominator here is from that from here. So the sum of the probability equals 1. So we get that from there. And this is just the probability of the power law degree distribution. So we know that this one converges. It's known as P-series, and it's known to converge when the beta is greater than 1, and which is the case here. But this one doesn't converge. It only converges when beta is greater than 2. So the average is not exact constant. So what we can do here is that we can further proceed with numerical computation, and then this shows how the speed of upper bound scaled by the data size is bounded in terms of size of data and the power law exponent. So to pull this bound upward, we need to add some positive term here. And that's what our domain decomposition accomplishes. We do that by splitting heavily loaded location into sub-locations. And we choose to split heavily loaded location into sub-locations rather than just distribute location data at a final granularity, because that's better for the scalability, handling, and addressing the data, and also for efficiently sharing data within a location, such as zip code or coordinate. So the plot on the top right side shows the estimate speed of upper bound scaled by the size of data for each state data of the United States. So we have 48 states in contiguous US and DC, including DC, there are total of 49 last year. And this is before the domain decomposition applied. And then after applying domain decomposition, we pull this as upward. We pull this scalability bound upward. So we do this, we achieve this by only splitting 5% of the locations. And this shows how the degree distribution and load distribution and estimate speed up changes as a result of decomposition. The top row shows the one before decomposition, and the bottom row shows that those after decomposition. So before the decomposition, some vertices had load of almost about million, while some load has only one. So there's huge variance in the load. So in addition to the domain decomposition, we also use various data distribution strategies. So we have, the example that we have here is that we divide 4 locations between 2 processors. So each location has zip code, location ID, and the estimated load by the model. And to split these locations between the processors based on zip code, we first sort the location by the zip code. And then for the same zip code, we sort the location by the location ID. And then we divide these locations evenly in terms of the number of locations. That's one method that we try. And the other method that we try is that we evenly distribute these locations in terms of the sum of the cost. That we denote that case as ZC here. And the lines here on the upper graphs connects the locations in sequence. And the dots shows the amount of location load estimated by the model. The size of the dot it's proportional to the amount of load estimated. So this one is for Iowa, and this one is for Michigan, and certain region is not really loaded. And in fact, there are 2 different types of locations in our data set. At least that's how we categorize them. So one is home locations, the other is non-home locations. So, and we treat them separately, but in the same way. So we first divide non-home locations and then divide home locations. And then we assign people data to their home. So if you see it here, this shows actually the state boundary. But here, it's actually some locations are beyond the state boundary because we want to include all the locations that people visit within the state. So people visit locations within 50 miles radius from their home. And based on this distribution, the first processor will have L1, L2, L3, and H1 and H2. And second processor will have L4 and H3 and H4. And the people living in these homes. So I'm going to show some performance results here. So this one shows the impact of domain decomposition and data distribution strategies that we just talked about. So there are more data distribution strategies. So RR stands for round robin, which mimics the random data distribution. And GP stands for the distribution based on graph partitioning. And Z stands for the distribution only based on the zip code. And GC stands for the distribution based on zip code and cost. And the split log stands for the domain decomposition that we talked about. The biggest impact here is from the domain decomposition. So among those with domain decomposition, graph partitioning performs the best, and the zip code and code space distribution performs closely to the graph partitioning. But the distribution only based on zip code ignores load balancing and does not perform well, such as these yellow curves here. So there are three schemes that optimize locality in some way. So graph partitioning and zip code cost-based and zip code-based. And there are two schemes that balance load, zip code and cost-based and graph partitioning. So this one shows those decomposition and distribution impact on load distribution. So the y-axis here is a processor line, and the x-axis here timeline. So this shows what each processor is doing over time. So blue represent the person computation, orange represent the location computation, and red represent the receiver's message handling. So as you can see, with domain decomposition, there isn't much peak with location computation. But without it, there are huge peaks. And even with domain decomposition, if you don't optimize for locality, there are peaks like that. And with graph partitioning, the person-phase computation is shorter because there's less interference for receiving the messages, because some communications are local. And this result shows the impact of domain decomposition and data distribution on the communication in terms of the amount of data received per processor in megabytes. So those plots on the right side is with domain decomposition, and the one left side doesn't have domain decomposition applied. So again, there's a lower peak with domain decomposition. And there are two schemes that optimize for locality, graph partitioning, and zip code based, actually three schemes, zip code and code spacing as well. So with those cases, the total volume of communications is less compared to the other case. But with graph partitioning, there are huge peaks like this. It's because graph partitioning minimizes the total edge cut rather than balance the cuts across the partitions. So this shows the largest strong scaling result that we have so far. This one is from the blue waters. On the top right one is from the Vulkan, BlueGenQ, and the one at the bottom is from some InfiniBand cluster with Xeon processor. So with blue waters, we achieve a strong scaling up to 300 using 352K cores. I think I was using almost 99.6% of the total XE nodes over there. But I wasn't using the XK nodes. And with BlueGenQ, I ran it up to 128K cores because of the resource limitation, not because of the machine size. The machine size itself is 3 times larger. And as you can see, there's a big improvement from TRAM compared to the other case. But in this case, TRAM wasn't available at the time, so I don't have that data point. And the difference between green, actually difference between red and the black shows the results of domain decomposition. And this is the weak scaling performance results. So here we have the results from Blue Waters and Vulkan and InfiniBand cluster. And the difference between green and blue shows the results that show the improvement from the domain decomposition, and the difference between red and blue, in this case red and green, and again here red and blue, shows the result of low-level code optimization that I talked about earlier. And in summary, we analyzed how the heavy-tail property of the input graph limits the scalability of the application, and we introduced an application-specific workload model as well as the composition method, and we enabled data distribution with the application-specific information, and we finally demonstrate the strong scaling that is 5 times larger than the best known so far, although it may be not the fair comparison because the previous best scaling was based on XT5 platform, but ours are based on XT6. So that's the end of the talk.
Questions?
For your, I guess, both sets of results, what was your configuration? Were you using threads and MPI? Or on top of Charm?
Yes,
within, and so how many threads or MPI tests did you have, particularly on BlueGene?
So on BlueGene, actually on both platforms, I used 4 processes per compute node and 12 worker threads per compute node. Actually, 4 worker threads per process.
Any other questions? Okay, let's thank Jason again. So we have 2 announcements. One, there's a small change in the program. We stop after Jim's talk and go for lunch, or lunch will be outside, and we'll resume after lunch with the program. And the other thing is we are planning to go out for dinner as a group. So if you're interested in joining us, Nikhil is going to pass around a sign-up sheet. So if you put down your name, we'll make sure you are around in the evening. So the next talk is by Jim Phillips from the Theoretical and Computational Biophysics group. This is one of our oldest collaborations, and Jim will talk about recent advances in NAMD.
Okay, so thank you very much. So, and I'm Jim Phillips. I'm the lead research programmer for our molecular dynamics code NAMD for quite a while now, and it's been a good year. So this is the HIV capsid simulation that we've gotten a lot of press on. The man largely responsible is Juan Perea, sitting here in the middle of the room, sort of hunkered down. And like I said, this went very well. So HIV is everyone's heard of HIV. It seems important, but why is this work really interesting? So just to let you know what's going on here, this is sort of how the HIV virus is put together. You've got the capsid, which is this protein shell, and then outside the capsid, there's another protein shell, then there's a membrane, and then the membrane has various proteins in it to fool the cell into thinking, okay, this is something that you want to let in. The way the infective cycle actually works is we have our little viruses here, so they have to bind to the cell, they have to fuse with the membrane, inject the capsid, and then the DNA, RNA from the virus has to be reverse transcribed and has to sort of infect the cell, take over the cell. You need to reproduce, more viruses on the way out to continue the cycle. And there are a couple small details that the capsid is responsible for. It's uncoding and actually getting into the virus. And I sort of want to explain, when you think of this capsid, yes, if you look at the picture, it's a big clump of proteins, but it's actually a very specialized structure. So I like to use a soda can as an example here. So if you think of this, there are lots of things you can put soda in. Why do we use this? Well, first of all, it's designed to not open randomly, so you can transport this all over the country, it doesn't leak. When you do want to get something out in the right environment, in the hands of the user, well, first of all, it looks like something that you want to drink. It looks appetizing. It doesn't, list the, the poisonous contents in large print. It's, Diet Mountain Dew. When it does get to the right environment, it opens easily. It dispenses the contents to the right part, onto your tongue, not, down the front of your shirt or onto the floor. When you first open it, it sends out a nice spray. It smells good. It sounds good. It hits the right part of your tongue. And then, to make more of them, it's very efficient in terms of materials to be able to put something this together easily and recycle it. So the capsule is not just a container. It's very an active part of the infectious cycle here. In particular, as I said, it plays a role in, it has to fall apart at the right time, and it actually plays a role in actually putting the RNA into the cell. How do we fight HIV today? Well, we've got drugs that try to prevent basically the virus membrane from fusing with the cell membrane. We have drugs that try to impede reverse transcription. The reason that these are called retroviruses is that the viral RNA is transcribed into DNA, which then goes into the nucleus of the cell rather than simply sending out RNA directly. Integration into the host genome, and we have drugs that try to prevent, protease that breaks off the new viruses. We have nothing currently that targets capsid uncoding or nuclear import. So having the structure of this virus really makes it possible to potentially develop drugs or understand what drugs might do when they interact with that. I'm going to let Juan, so the question is, will targeting the capsid create the most effective drug? And the answer from Juan is? So the short version of that answer was that, first of all, since there are no drugs that target the capsid, there's no resistance to a class of drugs that target the target. And second, in nature, simians are immune to HIV. And the way that that is achieved is that they actually have proteins which interfere with the capsid somehow. So it is a promising domain. Okay, so work like this, of course, takes a village. So we work right across the way here at the Beckman Institute. This is sort of Schultenville, and we have two main packages, a visualization package, VMD, and the simulation package, NAMD. Large number of collaborators, long history as a NIH-funded resource, which we hope will continue for some time going forward. One of some of the things that we have locally, we can't afford, our own supercomputer, but we have been assembling the infrastructure to be able to manipulate these kinds of simulations. So yes, we've got Titan or Blue Waters here. We need to store the trajectory. We need to analyze the trajectory. We need to be able to visualize this kind of thing. Now the problem is we can do this, but we're supposed to make this software available to outside groups. We let them come in and use this, but the direction that we really need to go, and I'm telling you because my hobby this year is telling everyone, we need to virtualize this infrastructure. So instead of making people get their own hardware, we have, the large-scale compute, we have storage, we need large memory analysis style computation, and more importantly, we need remote visualization capability integrated with the supercomputer sites so that rather than sending, needing a 10 gigabit link just to download the data, store it somewhere, all the work we've had to do, you just send compressed video just like you watch Netflix today, only slightly, higher resolution. So that's the goal right now. Texas is actually leading on the way on this. So the Stampede cluster has nodes that have 1 terabyte of memory. It's not, virtualization like is being worked on, but you basically allocate an entire node. It just works. They've got the new Maverick cluster. Blue Waters doesn't have a visualization resource. Titan nominally has one, but the new cluster they added doesn't even have GPUs on it, so that's not going in the right direction from our viewpoint. And I realize that there's maybe one person who does the molecular visualization in the room, but just performance analysis on this class of machine, doing the traces that you get out of projections and viewing those, this is a large memory workstation with an SSD RAID that I transfer the files onto, load them onto, and then I'm looking at it on this 4K display. It's really nice to be able to run the job, leave the traces on the parallel file system, and just load them directly when working on Stampede. So that's my little goal for the year, is to actually get some remote visualization resources onto Blue Waters. But so as we said, NAMD, we have to serve a large number of people. So the goals that we've had is that these are biologists, biochemists, biophysicists that we're serving. They don't need to understand how the program, well, it's not the laser, how the program works internally. We try to support, everything from desktops, so we teach workshops. You can come, learn things there, go from that to, your local cluster, campus cluster, to the largest supercomputer in the world, and really not even know what Charm++ is. So we try to preserve that, and it's available free of charge. So, we've also moved up the scale. Over time, this is what we've sort of been doing. Machines have gotten larger, the software's gotten more capable. We've gone from sort of single proteins to, small protein lipid complexes. This is ATP synthase. This is a little ratcheting thing that stores chemical energy in the cell. This was the first virus we did back in 2006, satellite tobacco mosaic virus. It's a virus, but it can only infect the cell that's already infected by another virus. So the tobacco mosaic virus is sort of the main virus, and if you've got that, well, then this virus piggybacks on another virus. The ribosome is the structure that reads your DNA or reads your messenger RNA and churns out proteins. If we can understand how this works, we can, this is different between bacteria and eukaryotes. So if we can understand how this works, this is what a lot of antibiotics target. And then finally, the HIV capsid. This was a 64 million atom simulation, the current thing. But what I want to point out here is that we're not doing larger simulations just because we can do larger simulations. We're not taking, 1 protein, 10 proteins, 1,000, 1,000,000 proteins. There's one of each of these things in here. And this is not a symmetric structure. You can't model, this one corner here and represent the behavior of the entire structure. This is asymmetric. You nearly need to do the entire thing to understand the mechanism, understand the dynamics, understand how this falls apart, understand how this operates within the cell. So we're not doing big because we can do big. We're doing big because biology is getting big, and this is the level of experimental data that's coming in. Okay, so back 2006, again, this was the first simulation. We actually learned something from this back then. If you take the RNA out, the thing collapses on its own. HIV, it's actually stable without it. People say, well, why do you have to do every atom? Why don't you do coarse graining? Well, we have done coarse graining, and you can do some things from coarse graining, but it's not that same. Life is basically put together atom by atom. Some things you have to understand the entire structure, and once you understand the entire structure and you understand the mechanisms, then in some cases you can put together a coarse grain model that lets you go to longer time scales more cheaply. But it's not a substitute. This is where we were back in 2006 when we first found out that NSF was going to be building this large-scale supercomputer that eventually became Blue Waters. So this was on Big Ben, which was running up to about 3,000 cores. They were single-core processors back in the day. So this isn't ambiguous down here. And here's the virus and the ribosome scaling up to pretty much that whole machine. It's been a long, strange trip. This is where we've gotten to now. So this is running on Titan in red, Blue Waters in blue, and the Mira Blue Gene Q up at Argonne in black. Note this is number of nodes. Titan and Blue Waters are sort of our main production platforms. I actually had to get some emergency access from Benoit Roux to even run these benchmarks on BlueGeneQ, but it works very well. It's easy to scale well when your processors are slow and your network is fast. But yeah, we've put a lot of work in this, and we're basically getting up to, this is a 224 million atom system, so this is over twice the size of the Blue Waters acceptance test, 3-4 times HIV, running up to effectively the entire machine. These are nodes, not cores. 14 nanoseconds per day, 80% parallel efficiency, which is really great. Smaller systems, we can go faster, not using the entire machine. And then we get a pretty decent boost out of the GPUs, but as you scale up, you lose some of the you lose some of that to the network, but the GPU version is still always faster. So yeah, and of course we owe a lot to Professor Calais and the Charm++ group. This is recognized. Professor Schulten and Professor Calais actually shared a Fernbach Award 2 years ago, and this has really been synergistic research. So there were requirements in NAMD which inform Charm++. Charm++ develops features based on those. We already have working features that do the same thing, so we ignore that for about 10 years or so. And eventually, after we believe it works, then we start filtering some of those things in. But really, there's a lot of back and forth. And also, as you've seen, the software works at scale for very challenging problems. So we use Charm++ basically as a parallel C++ with data-driven objects, asynchronous method invocation, prioritized scheduling of messages and execution is important for performance, measurement-based load balancing, and again, as a portable messaging layer, being able to optimize better than MPI for the Cray and the IBM networks. The design in AMD goes back quite a ways, and it was evolutionary or revolutionary and somewhat underappreciated at the time that we have these spatial domains and sort of independently separate the decomposition. So it's not purely a spatial decomposition, it's a hybrid space and work-based decomposition. The data domains pretty much stay put, but we can dynamically load balance the work. And then overlapping execution. So during a time step, we have sort of these bonded terms that represent covalent bonds, the non-bonded terms, which are pairwise, and then long-range electrostatics is implemented through particle mesh AWOLD, which is a fast Fourier transform-based method of doing long-range electrostatics. This is the latency limiting stage, so this is shown as a two-dimensional slab or one-dimensional slab decomposition with a single transpose for larger systems. We use a two-dimensional pencil decomposition that has 4 transposes, z to y to x to y to z, to do this calculation. And we can overlap this, and this all hides. When GPUs came around, the pairwise objects are by far the most expensive part, so we offload that to the GPU. We were sort of early adopters for this, and we can overlap communication and computation on the GPU with the CPU, transferring positions, running some of the forces in parallel, doing the local forces last so that we can communicate forces and positions. This is the actual timelines from what's going on there. Again, position transfers, upload to the GPU, run on the GPU, transfer the forces back, and then receive the local forces locally and continue immediately with integration. Okay, so getting from the million atom virus to 100 million atoms was really pretty challenging. Just the million atom simulation, when we did that for the first time, it was sort of a natural extension of the tools that we had. It fit within the memory of the machines. Runs a little bit, it ran slower for some parts, reading the file, but it pretty much just works. To get to 100 million atoms, we had to fix a lot of things. We have new file formats. The molecular structure doesn't fit in a single node's memory anymore, even in SMP mode, which we were already doing, so we have to distribute and compress that. Input data, shared memory, lots of change there. We also had to put together the benchmark that was supposed to run on this because it was specified as a rather vague paragraph. So that's just for 100 million atoms. Then getting up to 300,000 cores on Blue Waters. Turn++ shared memory, Tune for Power 7. They changed the machine from Power 7 to Cray. Tune for the Cray network. Replicas to be able to do different simulations for smaller things. Optimization for physical nodes in the machine. A whole lot of stuff. Plus, oh yeah, they wanted, we need to run on GPUs. So lots of work goes into this. Some of the more recent work, I just want to highlight adapting to the torus topology of the network. It's relatively simple-minded, but it made a pretty big difference in some cases. When you run on a BlueGene, you sort of get this irregular torus network. So if you imagine here, you've got gaps in it. It's not like a BlueGene. You might have other nodes running at the same time. The first thing we do, we take the nodes we're assigned, we rewrap that to the most compressed set. So you might be, big gaps in the middle. We rewrap that. Then we just do a recursive bisection, both on the nodes that we're given. So we'll take this curve through the nodes, divide in half, and then in the next direction we'll go the next longest direction. We do this to both the torus of the machine and to the patches that are in the simulation, and pair those up. And that gives us a good mapping between the structure. We have minimal work that's on each physical node, and then we pair this up, and it makes a pretty good difference. So running on Titan at the largest scale of the machine, we actually see a 50% performance increase from doing that over sort of what the machine default node ordering is. What we had found before this was the Turn++ node ordering is if we just sort of have the nodes sorted along one dimension rather than the space-filling curve that the Cray seems to use by default. We can make that worse, and if you want it to be even worse, if we just sort of totally randomize the topology and the node ordering of the machine. So on the Cray XK7 network, topology definitely makes a difference, and we can make it better and we can make it worse. So we know now how to make it better. So this was a nice improvement. Again, as you get smaller, it doesn't matter as much unless you consciously try to make things worse. One note for those benchmarks. When you do runs on these platforms, you get great variation in your performance from run to run. Particularly, you might get different allocations, so you might have different shapes, different parts of the machine. There are other jobs that are using your links, so you can't just sort of run once, case A, then submit another job for case B and keep comparing. You really have to run everything back to back in the same job on the same allocation to really get comparisons. So that's what we had to do, which makes these studies a little more expensive. BlueGene-Q is a 5-dimensional torus. Makes absolutely no difference what we do with the torus, with the topology on that machine. It's exactly the same. So, well, topology may have been a little bit more important on L and Q class machine, L and P class machines for NAMD. For BlueGene-Q, we're not seeing that much of an effect at all, which is really a strength of the network. So the CUDA kernel, so PME, I mentioned before that for particle mesh AWOL, we've been doing that on the CPU and only offloading the non-bonded. When we went to the 100 million atom simulations, the PME communication and FFT really became a bottleneck. And sort of the breakthrough for that was realizing, well, we're using this sort of standard 4th order interpolation, so every charge ends up in a 4x4x4 cube. If we switch that to 8th order interpolation, well, yes, you get 8x8x8, which is a factor of 8 more points for each charge, so that work goes up, but you can cut the size of the grid in half, so you have a factor of 8 less data that actually has to go across the network. So that's actually a big improvement on that critical path. When you do that, you're putting more work into doing that gridding and ungridding. So if you offload the most expensive part to the network, that can still be significant, and in particular, we're offloading, you want to get the data on the network as fast as possible so we can feed that up. So we put together sort of very, basic Kepler-optimized kernel for doing that. The first time we tried it, it was actually slower than just doing the PME on the CPU completely. Initial plan was, okay, for every patch, we'll submit a CUDA kernel. Those kernels can run on the entire machine and get back. There's just too much latency on the GPU to be able to launch that. So, okay, we fixed that. So instead of 1 per patch, it's 1 per PE. Now we're launching, 8, 10, 12 kernels per step to do this. Still not quite faster. Then we realized, okay, this is all running on the same GPU. We can sum everything into the same charge array, and that's actually faster. And part of the reason for that may simply be that we're also sending fewer messages per node. So rather than having each PE on the node sending its data to the corresponding grid locations for the FFT, we're sending 1 message per node to those grid locations. So that is a potential source of the optimization that we can now backport to the CPU version. What we actually get out of that, so I mentioned coarsening the grid and doing higher order interpolation. This is how much you lose by turning off various optimizations. We turn that off, we drop by a factor of 2. If we don't offload to the GPU, we drop by about 20%. So this was the big improvement, was actually getting to that coarser grid. Then you get a small boost from offloading the interpolation to the GPU, and about a 10% boost from reducing some synchronization in the constant pressure integration algorithm. So what did we learn from all this? So basically, the lesson is that optimizing communication is job 1. In particular, this is sort of a new pet peeve of mine. There are lots of things where, okay, I need to write a broadcast tree. Well, if I 0 sends to 1 and 2, 1 sends to 3 and 4, 2 sends to 5 and 6, this ends to 2n plus 1, 2n plus 2 pattern. If your nodes are arranged at all sanely, this is sort of the worst possible thing that you can do. Because first of all, most of the first stages of broadcasting are all within a single node. And then everybody on that node is sending the same message multiple times to other nodes. And even worse, if you look at the topology of the machine, you're sort of, broadcasting on the left half of the machine, spreading out, and then the entire left half of the machine sends to the entire right half of the machine. So if you instead send far away first and do the broader stage of the tree locally, the way that you would normally write a tree, works much better. And this, things like this were actually causing the network on the Cray to throttle, which is when the network freaks out because there are too many messages and says, okay, nobody sends anything more than a single node can process until we drain the network. And then you sort of find out after your job is run that this happens. So very bad. Other than that, basically avoid sending messages unnecessarily between different physical nodes in the machine. Within a physical node is not as bad. Ideally, sending data within a node is virtually free. And again, doing that. As far as lessons learned, otherwise, incremental development is entirely possible. You don't have to rewrite the entire machine. Yeah. You want to go from working code to working code. Memory issues you can fix as they arrive. Definitely use profiling. Profiling will tell you what the problem is, but it won't tell you what the solution is. It was really sort of insight that led us to the PME and load balancing issues. Be careful about major rewrites. You really need to understand what you're doing before you want to put in that kind of effort. As far as Charm++ goes, I was sort of gratified to see that other talks today have had a similar lessons going on, similar types of things. The programming orientation really needs to switch from thinking about PEs to actually thinking about nodes. So thinking about programming the entire memory space. For one thing, you have shared data that you really want to share at the node level rather than distributing at the PE level. Lots of codes do that. Parallel I/O, you want to distribute that across nodes and physical nodes. You have various offloading processors such as GPUs or mic processors. Those really have to be managed at the node level. You can't multiplex things from every host thread onto these. Dynamic load balancing with a node should be pretty much free. And finally, the change that I'm looking for is to be able to have array elements rather than being mapped to specific PEs. able to process entry points at any PE in the node. So we have node groups now, node arrays, finally. One thing that I've also noticed people doing is like, well, we need better support for execution fences. So there are lots of cases where, if we start X, it's going to lay Y because X has some long-running elements. So we need to add fences so we don't start X on the PE or on the node until all of such and such from this phase has happened to avoid delaying it. So we do this for computes. Don't launch any computes until all the patches are ready. Don't launch any computes until all the proxies are ready. Don't start the GPU non-bonded work until you've launched the PME work. One property is these are pretty much exclusively used for performance reasons, not for correctness. So people write the code, that allows these, they observe this is happening, then they fix the performance issue. Features like this would also enable MPI-style sequential programming. Okay, so thank you very much to many people, and again, Juan, responsible for the HIV work, is in the room, and I assume he's going to lunch. So, if you have any questions for him or for me, thank you.
Thanks, Jim. We can take a few questions.
Yes.
Very non-technical. Talk about how talking about the treatment and assume there's mass
We'll get you a microphone. So the question was sort of, how does the free world of the science and the software mesh with actually developing HIV treatment?
So we work with, these are 3 big collaborations that are funded by NIH. Some of them have collaborations with pharmaceuticals like Pfizer and Boehringer Ingelheim. So there is like an ongoing effort to develop new drugs, and we're part of that. It's a collective effort. It's pretty big, actually. They put on resources, they put scientists, they put good sense of that. Oh, I think this is more general than.
Yeah, there are layers and layers in this collaboration, from the experimental groups down to the scientists who are running the simulations, to the developers for the software, all the way to LA. So it's yeah. Well, this is just for NAMD. I mean, I've got a whole other slide somewhere for the. See if I can find that. Yeah, so this is sort of the direct HIV acknowledgement. So we've got the local work, excluding lots of people locally who have helped with this, and the whole NAMD team, and then the different experimental teams that contributed to the Nature paper.
So we'll stop for lunch now. It should be outside. And before we convene here again, we'll have a group photograph at 1:15 somewhere in the lunch area, and then we'll start at 1:30 again.
So as a side effect, the evening session will be a 2-hour session from 3:30 to 5:30. So one of the talk has been moved there. And all this primarily because Thai food tastes much better when it's hot.
Any one of you who's got hang tag from us, please just contact me for a useful piece of information. Basically, you need to be parked in a metered spot with Illinois written on the meter. So it cannot be an Urbana meter, it cannot be the parking lot.
this point, may I request everyone to move towards the stairs right outside the room so that we can take the group photograph. So we can first do the full workshop thing. Yeah.
So. We're going to start in about 10 minutes, is that right?
Hello? Yeah, that's right. We were just taking the group photograph, that's why I was not here.
Okay. Hi, Abhishek.
So, sorry? I think so. Yeah, we'll leave him open like this. And do you have any slides you would be presenting, Dehan?
No, I will be just speaking.
Oh, that's great. Okay. So that's set up. And there's no echo. Do you guys hear any echo at the back of this room today? Oh, that's great. Okay. So that's awesome.
When it comes 15 seconds later.
So yeah, if you hear the same question again after 15 seconds, let me know.
Should we do something about it?
Dehan, can you see the slides?
Yes, I can see them.
Okay, that's great. So we'll probably start in like 7 to 8 minutes. There's still some time. So.
Okay. Thank you. Thanks for keeping me in the loop.
All right. Welcome to the afternoon session. This session is about cloud computing and HPC. We will begin with a talk by a PPL graduate student, senior graduate student Abhishek Gupta, who's been working on cloud-related work. Started with his internship at HP and so that led to a collaboration. And then, as you heard yesterday in Suraj's talk and other talks, that there are features in Charm++ that make it suitable for exploiting the cloud environment. So, we'll hear about Abhishek's work first, and then he will chair the rest of the session. Okay, Abhishek.
Thanks, Sanjay. So, in this talk, I'm going to give a short overview of our research on HPC in the cloud. First of all, we have heard a lot about HPC, but how do we define cloud computing? There have been a lot of definitions of cloud, but one of the most acceptable definition is the one which is provided by National Institute of Standards Technology, NIST, and that defines cloud computing as a model for providing computation or storage or other things as a utility, as a service, with having essential characteristics of on-demand self-service, elasticity, resource pooling, multi-tenancy, which means that multiple users would be sharing the cluster or the physical node as such. And then there are various deployment models, such as public, private. Public means that pretty much everyone has access to the cloud. Private means it's restricted to the organization. And then there could be a mix of those, hybrid and community. And the service that is provided by the cloud provider could be just infrastructure, which is physical or virtual compute, storage, or network. For example, Amazon EC2 and HP Cloud and others. And on the top of that, there could be platform as a service, which includes more programming language execution frameworks and so on. And on the top of that, there could be software as a service. But why do we want to consider cloud for HPC? Consider yourself as a small or medium scale user in academia or in industry. And if you have limited or no access to supercomputers, then for the option for you is either to create your own cluster, which requires significant capital expenditure, setup time, and operational cost, or you can go to cloud using a pay-as-you-go model. So there are advantages of this renting versus owning an infrastructure. And there are additional advantages that comes in the form of elasticity, which is especially useful if your demands are sporadic or unknown in advance. And there are also some benefits of virtualization that are offered by clouds for HPC. So overall, cloud for HPC appears to be a promising alternative to supercomputer, but whether that can be actually realized in practice or not, that needs to be seen. So you wanted to evaluate the performance of various HPC applications on a range of platforms, varying from supercomputers, and we use Ranger and TOB. And then we also use a physical cluster, OpenCirrus, which has commodity interconnect. And then we use private and public two clouds. Both of them have used KVM as virtualization mechanism. And they have like a gigabit physical Ethernet, representative of common commodity clouds. And we use various benchmarks and applications, NAS benchmarks, and then real applications, NAMD and Changa, which you have heard about in previous talks. So when we did this performance evaluation, we saw 3 different performance trends. So for some applications, we saw that they scale well on pretty much all the platforms. And so over here, we have execution time versus number of cores. And the applications such as NP, state space search, embarrassingly parallel, and Jacobi stencil computation, they scale well on clouds as well. For some applications, they scale well till a particular point of time, say 16 to 64 cores, and then they stop scaling on the public and private clouds, the blue and the black lines. This is like Cosmology, Changa, and then similarly for NAMD and LU. And then for some other application, they did not scale at all on clouds. So for example, this is NAS Speller benchmark integer sort application. So So this is total is 256 cores, and individual nodes are four core nodes, but it differs from platform to platform. For example, some of them have different cores. Ranger say had 16 cores per node. But we use non-SMP for the case of charm application. So what are the reasons why we see these different trends in different applications? So that's the objective of this research. And the bigger objective is, once we realize what are the bottlenecks or what are the challenges, then how we can bridge that gap between HPC and clouds. And our philosophy is that we can bridge that gap by either improving HPC performance, or the other way to go about is also to try to improve cloud utilization, thereby trying to reduce cost for running those applications. So the outline for the rest of the talk, I'm going to discuss the challenges and opportunity that we find through the performance analysis. And then I'm going to talk about two particular techniques that we have come across as part of our research. So the first one is application-aware cloud scheduler, which is about trying to make clouds to be HPC aware. And the second one is more about making HPC runtime, such as Charm++ in our case, to be cloud aware. What we can do to get better performance in these sort of dynamic cloud environments. So to find more about like what are the bottlenecks, we did some micro benchmarking for using ping pong benchmarks to find the communication performance in different platforms. So over here we show the latencies, and we see that the blue and the black curves, they are about 250 microsecond of latency as compared to supercomputers, in this case Ranger, which is about 4 microsecond of latency. So it's about 2 orders of magnitude off compared to supercomputers. And similar trends hold for bandwidth. But what are the reasons for that difference? And the difference could be either commodity network in the case of clouds, or the virtualization overhead. And it turns out that the difference is coming because of both the reasons. We see here that the green curve, which is the physical network performance in the case of OpenCirrus, which is a commodity platform. So that itself is 50 microsecond, and if you compare that to say 4 microsecond of Ranger, that itself is an order of magnitude difference. And on the top of that, there is virtualization overhead. So here we are showing 2 different virtualization mechanisms for latency comparison. And we see that we get about 150 or 200 microseconds of latency if we consider virtualization. And similar trends hold for bandwidth. And so this led to a collaborative work with HP Lab Singapore, where we explored the use of thin virtual machines and Linux containers to reduce this network virtualization performance. So the blue curve then comes very close to the green curve, and you get pretty much bare metal network performance. So another trend that we saw was and which I should have emphasized, was that the public and private cloud also we can see performance difference for the applications. But here the network performance is pretty much the same. So that's not the reason for the difference in application performance in public versus private cloud. And it turns out that the reason is multi-tenancy. So multi-tenancy means that there are multiple users who could be sharing the cloud infrastructure, and that it could be also at the cluster level, but it could be at a final level, that is at a node level. So the same physical node could be shared by different virtual machines from different users, and the sharing could be at the CPU core level, or it could be they may not be sharing the CPU core, but they may be sharing the same physical node. So there's interference that comes because of that. So this multi-tenancy hints towards a bigger divide between HPC and clouds. And the fact is that HPC systems are designed towards getting the maximum performance with some constraints such as energy and so on. But cloud is more about cost and service, providing service and having improved resource utilization. And from this fundamental difference, HPC prefers dedicated execution, cloud prefers multi-tenancy, and similarly we have the difference in the networks in HPC versus cloud. And overall it's like HPC is not cloud aware and cloud is not HPC aware. And because of this mismatch, there are only embracingly parallel or small scale HPC applications that seem to be working promisingly well in the case of cloud. So how we can bridge that gap? So the first technique that we explore is to make cloud schedulers to be application aware, and we're trying to address the challenges of heterogeneity in multi-tenancy. So there's also heterogeneity in the case of cloud, in the sense that clouds are built incrementally by adding new nodes as they come. So the type of nodes in the cloud infrastructure, they could be heterogeneous. And for HPC, it's a problem, because especially for iterative applications. And similarly, multi-tenancy also results in this dynamic kind of heterogeneity. But one thing that is kind of less explored is, besides the challenges, cloud can also provide unique sort of opportunities for HPC application. And one of the opportunities is virtual machine consolidation. That is, you can have virtual machines of different types on the same, with different application characteristics that could be put on the same physical node. And we explore how or whether that can be beneficial. So the main trade-off, as I said, is HPC performance versus the resource utilization in the case of cloud. So if we want to place multiple VMs from different applications on the same physical node, how much interference that can result in. So to quantify that interference, the amount of that interference, we did a simple experiment where we ran applications in two different modes. One is the shared mode and the other is the dedicated mode. So in case of shared mode, what we do is we run two different applications on each node. So each node is a 4-core node here. So in the shared mode, we use two virtual machines of each application on the same physical node. So the total number of cores, the total number of processes or cores are same in dedicated mode versus shared mode. So in the dedicated mode, so if it's a 4-core node, then all the 4 cores are used for the same application. Whereas in the case of shared mode, there would be two cores for one application, 2 cores for the other application. And similarly, the second node would have 2 cores for one application, 2 cores for the other node. So the VMs are not sharing the core among each other, but the physical node itself is being shared among different virtual machines. So then we plot the normalized performance of different application combinations, which are shown on the x-axis. Each bar in a particular combination is for one of the applications of the two. So we see that as expected in many of the cases, there's interference. So for example, in the orange arrow, the LU and integer sort, when we run them in a co-located fashion, we get poor performance for integer sort. But the interesting observation is that we also see some scope, or we see some better performance in some cases. For example, the one marked scope, where EP and LU were run in a co-located fashion, we saw that the performance of LU actually increased, whereas the performance of EP was not that much affected. So we dig deeper into that, and we use performance counters to measure the different characteristics. And we saw that there's a correlation between the last level cache misses per second and the shared mode performance. So the reason is that by intelligently placing different applications with different characteristics, you can get a better utilization of the shared resources such as last level cache in a multi-core node. Because if you can place an application which is high on cache usage with an application which is low on cache usage, then the performance of the application with high cache usage can actually increase. So with this observation, then the philosophy of or the technique for incorporating this in cloud schedulers is to characterize applications along these two dimensions. One is the cache intensiveness, which assigns each application a cache score based on the measured last level cache misses per second, which is representative of the pressure that they put on the shared resources. And then the second characterization is the how much network communication that application performs. Because in the previous slide, even though, so even in the case of LU in integer sort, the integer sort performs poorly when in a co-located fashion. Because as we are running it in a shared mode, we are spreading it across multiple nodes, and encounters more communication. So with these two characterizations, then we co-locate applications with the complementary profiles. The idea is to use dedicated execution, that is no sharing, for extremely tightly coupled kind of HPC application. Whereas for the rest, we perform multi-dimensional online bin packing. So there are multiple dimensions because when a user requests a virtual machine, you can specify like I need VMs with this much CPU and this much amount of memory, and then you want to pack those requests into physical hosts. So the physical hosts also have these dimensions, memory and CPU. By using this multiple dimension bin packing, you can actually fit more. For example, one application which needs more memory, you can fit with another application which is more CPU intensive. And to address the challenges of the interference, we use the cache characteristics and the strategies that the cache scores of all the applications on the same machine, same physical node, should be less than a particular threshold. So this results in improvement in throughput by 32%. Another technique that I'm going to briefly talk about is cloud-aware HPC runtime, which is more of an interest here, is that consider from a perspective of an HPC user, and you have no control over the cloud system, and you are given an infrastructure and allocation, and what you can do to improve your performance. We are addressing the same challenges, heterogeneity and multi-tenancy. The multi-tenancy results in dynamic heterogeneity because the interference in the case of cloud is random, unpredictable, and it also varies from run to run. And since you are running in virtual machine, it's further challenging because it makes it difficult to determine whether the imbalance is coming from the application itself or whether it's because of the extraneous factors. So in this case, this is showing a simple timeline where x-axis is the time, y-axis is the CPU, and we occasionally see elongated bars for the same objects, same computation. This is because some external virtual machine was interfering with the same, So existing HPC load balancer pretty much ignore this effect, and so we developed the approach where we consider this background interference, and then we dynamically migrate objects from overloaded virtual machines to underloaded virtual machines. So the technique is to address the static heterogeneity. We estimate the CPU capabilities. Since we are running in virtual machine, we don't really know like what physical hardware it is, but we estimate that using simple computation loops. And then we adjust the dynamic heterogeneity by instrumenting the time spent on each task, but also the time spent in background task. And there's some inaccuracy because you cannot accurately estimate the background times because you're running in virtual machine. But it turns out that if you do it periodically over and over again, this refinement-based approach of moving objects away from the time-shared VM to underloaded VMs, this works well in practice. I'll skip some of the mathematical details, but so one of the results with Stencil 3D, and here we set up a cloud on OpenCirrus testbed using OpenStack. So the red curve is without load balancing and the green curve is with load balancing. And the interference was applied between 100 to 300 iteration. And so with this load balancing technique, then the iteration time and the x-axis is the iteration number. So the iteration time comes down. And even after the interference goes away, we see that there is a difference between the red and the green. This is because of the physical heterogeneity which is present in the infrastructure. So our load balancer takes into account that as well. So this approach of periodically measuring idle times and migrating load away, this works well in practice. We tested with different benchmarks in application, resulted in 40% benefits. So finally, the conclusions of some of our research in this space is we started with the philosophy of finding who, what, why, and how of HPC in cloud. That is, who are the potential users that can benefit, what are the applications that could be run, why one should choose or not choose cloud for HPC, and how HPC in cloud should work. So some of the answers are, for the who question, we believe that small and medium scale organizations which can benefit from pay-as-you-go benefits, and then also those which have applications which can result in this best performance and cost trade-off, because there's also cost which comes into picture, which I've not really talked in this talk. But for the what question, the applications with less intensive communication patterns, which have less sensitivity, noise, and interference. And then I believe that it can work to small to medium scale, but for high-end HPC, you always need supercomputers. So clouds can be suitable for some HPC applications, but not all HPC applications. And some of the techniques that can work well is to use lightweight virtualization, and then making cloud schedulers to be HPC aware, and then cloud HPC runtime such as Charm++ and MPI to be cloud aware. And some of the models that can be used is to have a cloud as an addition to supercomputers, but not as a substitute. And there's a potential multi-platform approach where you have multiple types of platform. You can have, one can have a supercomputer, one can also have a sort of physical cluster, one can have a virtualized cloud. And based on the application characteristic, then you can select that suitable platform. So that's all I have in today's talk. I'll welcome questions, and then we'll after maybe a couple of questions, we'll start with the panel discussion on the same topic. Thank you for listening. Yeah, that's another. That's what I have not talked about in this, but that's another interesting direction. And I think we'll learn more from the panel about that. I certainly had that question to ask to the panel. There have been there have been at least 1 or 2 papers where IBM actually tried renting out BlueGene using a cloud model, and they estimated like what would the prices be if they were to rent it out using cloud model. You have the same slide.
Okay, so
So they need to be in the corner.
Right, and they're not going to be on the. How many here? You can pull a chair and see that.
Yeah, that table doesn't move. That's the problem.
No, I just want to be able to. I will sit there. That's very good.
Yeah.
I'm just waiting for President Chile. It's like the bank philosophy call it. I'll take it into Scott.
Okay. So we have the panelists here, and it's my great pleasure to introduce them to you. First of all, Professor Roy Campbell leads the System Software Research Group here at UIUC. He is the Sohaib and Sarah Bassi Professor of Computer Science and also the Director of NSA Designated Center of Excellence at UIUC. He is the Director of the Center of Advanced Research in Information Security. He is an IEEE Fellow, and he has supervised over 44 PhD dissertations, 124 MS theses, and an author of lots of research papers. Dr. Kate Cahey is one of the pioneers of infrastructure cloud computing. She leads the development of Nimbus project, which provides an open source infrastructure as a service implementation, as well as an integrated set of platform level tools, allowing users to build elastic applications by combining on-demand commercial and scientific cloud resources. She's a scientist in the Distributed System Labs at Argonne National Laboratory and a fellow at the Computation Institute at the University of Chicago. Dr. Dehan, who is attending remotely, is a senior researcher at HP Labs, Palo Alto. He's the IEEE Computer Society 2014 president, and he has been on many conference program committees and general editorial boards. Dehan is an IEEE fellow, ACM distinguished engineer, and Usenix member. So he's going to attend remotely as could not come on this short notice. So Landon Curtin-Hall is a resident astronomer and HPC specialist. So by day, his Cisco responsibilities encompass high-performance computing, security analysis, and standards. By night, he serves as an astronomer focusing on inner solar system as well as origins of solar system throughout our universe. He's the N in the widely used FNV hash, and as a mathematician, he developed or co-developed several high-speed computational methods, and has held or co-held 8 world records related to the discovery of large prime numbers. And finally, Professor Lakshmikant Kale or Sanjay Kale, you are pretty much all know. He's the director of Parallel Programming Laboratory and professor of computer science at UIUC. He has been working on various aspects of parallel computing with a focus on enhancing performance and productivity via adaptive runtime systems. His collaboration include the widely used Gordon Bell Award-winning biomolecular simulation program NAMD. He and his team recently won the HPC Challenge Award at Supercomputing 2011, and he is an IEEE fellow and the winner of 2012 IEEE Sydney Funwell Award. Okay, so we'll have we plan to have a very lively discussion. So initially we'll have a few minutes. We'll have each speaker present their thought on this particular topic for a few minutes, and then we'll break out and want to have a very lively discussion with all the audience asking various questions on HPC and cloud. So I think I'll...
So to professors, you don't say few minutes. You give them a time. Say 5 minutes, maybe.
Yeah, so we'll have 5 minutes. So I'll first...
You start.
Yeah.
Which order you want to do?
I think we have the order, the same order. So I'll invite Professor Campbell. Or we can have...
Set the tone. Oh no. Well, I'll try and set the tone. But, so I've been doing cloud computing for 8 years or so, looking at different aspects of it, and we have 3 different clouds on campus. And I also, in my teaching, I'm using Amazon quite extensively. I teach a couple of cloud courses, one at the undergraduate level, one at the graduate level. So I also use the cloud for my own research, and some of that's to do with doing bio. It's really doing the recomparison of genetics, and so been looking at all these things quite extensively. So some observations. I think most of the problems we always get is memory. Memory seems to be the bottleneck in all of the different computations, whether it's HPC or whether it's data intensive or whatever. We solve that problem by going parallel, essentially, and the different architectures that we discuss allow you to go with less or more sharing, depending upon what the nature of your problem is. I think the cloud computing is aimed deliberately, I might add, at low-cost computing efforts. And one of the bottlenecks you see in all the universities is that everybody is crying out for using computers, using lots of parallelism to solve their problems, even if they're not tackling the big Nobel Prize-winning major issues. Their research usually addresses quite a lot of computation, and they need that facility. And unfortunately, the universities are, at the moment, unable to provide quite the capacity that the researchers would like. There's several solutions to that, but clearly the solutions have to fit in an economic cost model. And so what is happening within all the universities I observed anyway, is that people are consolidating their computing facilities. This may or may not be a mistake. One of the issues is, can you actually build it like critical cloud infrastructure locally within a university campus cheaper than you can actually go and buy outside? And I think one of the funding issues for NSF is just, how do you provide? You still would like to provide the high-end HPC computing so that people can win the Nobel Prizes, but you also need to provide this general computing for scientists. And they are struck, if you like, by a third direction that's occurring, which is that as we proceed, we're producing bigger and bigger data sets. And those data sets are really oriented very differently from HPC. So all of a sudden, our data sets are big enough that the data dictates where you want to do the computation. You're not going to move data from one place to the other. So if you have, for example, the Sky Observatory data in one place, you're unlikely to ship it to somewhere else for a computation. You're more likely to bring the computation to it because it's going to take you days to get the data from one place to another. I think there's other areas where this same phenomenon is occurring. So what this gets down to is, for the university purposes, for research purposes, we need infrastructures. We need them to be very flexible. We may own our own infrastructures, but we will certainly want to exploit shared infrastructures. And we also want to start providing systems where we are orienting computation around data itself. And yet we need to do this in the most cost-effective way, which means the resources we choose are going to have to be essentially mass-produced, mass-designed, sold for all sorts of purposes. Hence, there is a huge incentive for us to try and exploit cloud computing whichever way we can within this approach. Now, there are all sorts of realms of the exploration one can do to make cloud computing improve the computation rate. But remember where the, if you like, the cost performance issue is. If you have a supercomputer, you're running it at 70, 80, 90% utilization because you paid a lot of money for it. If you're running a cloud computer, you didn't pay so much cost, so you can afford to run it at a less expensive rate. On the other hand, with a cloud computer, you're certainly going to have to think about how you can make it much more parallel and have much less computation. And is that kind of feasible? What innovations, what technologies are around the corner that will change some of this attitude? Well, for a start, the networks are going a lot faster than they used to. That's still not going to change moving data, but it will change how you can connect systems together. The other aspect is memory. Memory is going to go, there will be faster memories, but there will also be faster mass stores like SSDs that have really high bandwidth storage, really high bandwidth access, and then you will have specialized processors like FPGAs, GPUs that can accelerate computations. And so you're going to build systems that could be hybrid. The question is, how do you build an infrastructure, mass, cheap, inexpensive, but you can build these various different styles of infrastructure and manage it very easily with minimum amount of effort and some sort of consolidation in cost. And I think cloud computing does offer a way to do that, but as you will hear from all the different diverse views we're going to hear, we need some sort of organizing principles, some better software tools, some better software analysis, and a lot better understanding as we teach courses on what type of architecture is best suited to what type of computation.
Okay. I think the next speaker will be Kate, Dr. Kate. And then we'll have Dehan, and then Nandin, and then Priscilla.
Okay. Okay, so as Abhishek said, I am from Argonne National Lab, and at Argonne National Lab are created and lead the Nimbus team. About 10 or so years ago, we started exploring deploying virtual machines on remote resources to make it easier for application scientists to use what was then called grid computing. Right, so we more or less specialize in the type of research that is driven very closely by application needs. We saw that it was difficult to use grids, to use remote resources, because they were not configured to support your application, and also they were not available at the time when you needed them to be available. So we combined virtualization with remote execution. And that's what we call today infrastructure as a service cloud computing. Nimbus is a system that came out of my group. It was the first open source implementation of infrastructure as a service. But these days, and for the last several years, we've been focusing more on platform. So what Abhishek in his talk called the platform as a service level. In other words, providing tools that make it easier for scientists to leverage cloud computing cycles. And why was that needed? So more and more science is needing on-demand availability, on-demand cycles in the cloud. And in particular, I work with many environmental scientists or many GIS scientists, and they are processing large amounts of data that come from all sorts of sensing devices, from maybe iPhones sometimes, from sensors deployed in the field, from social networks even, and so forth, trying to filter, understand, and correlate that data and provide feedback in the system. So to give you an example, I worked with the Ocean Observatory Initiative project, which was a very large, 400 million funded project in ocean sciences, that is essentially changing the nature of the science from an exploratory science where you go out to the ocean and gather artifacts and reason based on them, into an observatory science, when you put sensors in the ocean and observe those sensors on an ongoing basis. Right? And some of those sensors are reactive sensors. So for example, there are floats which you can say, I don't want you to be here, I want you to be in a different place based on the phenomena I observe. And in general, this is becoming more and more popular because the sensors are getting much cheaper than they used to be. And also because very common sensors, like our cell phones, can become sensors for things that we couldn't imagine there used to be. Right? So recently, somebody showed that you can detect earthquakes because there's a way to distinguish earthquake-induced form of shaking of your cell phone from other forms of shaking, right? This solves a huge and very costly deployment problem for earthquake scientists, right? If they can get data from the cell phone. Their sensors are used in hydrology and all sorts of sciences. And now getting those huge amounts of data, so I like to draw the analogy between LHC, which everybody knows, Large Hadron Collider, the huge device built in CERN, and those sensors that we are putting in the oceans, in forests, and in our cities, and essentially instrumenting our planet. We're building ourselves a huge sensor that is hugely larger, right, than LHC. Right? So you can imagine LHC as having millions of sensors, and these sensors now leave the lab, right, escape, and start multiplying at large, right? And you get orders of magnitude more sensors, and somehow you have to process the data from those sensors on the fly and in a highly available manner, right? Because one way this sort of instrument at large differs from the traditional type of instrument is that you don't have a discrete start and stop experiment times, right? The experiment is ongoing. When you're observing the ocean or you're observing what happens in a city, the pollution and so forth via some sorts of sensors, it's going on all the time. You don't get a break, right? If you get a break, your system goes down, you start losing data, right? So this on-demand availability is becoming more and more important to a range of sciences. And many of the computations used by those sciences are high-performance computing. Right? So I work with hydrologists, for example, and they do require relatively tightly coupled computations to process and give them, from models that process hydrology, give them answers on demand. So how does cloud computing fit into HPC, right? Are we going to eventually end up with two different models where we have something that is on demand but maybe not very high performance and not capable of supporting those tightly coupled computations? And then on the other hand, we're going to have something that is, fairly traditional batch-oriented approach, right? and doesn't include virtualization and so forth. I think that long term, and of course it kind of depends on how you define long term, those two trends are probably going to fuse in some way. So a few years ago, I wrote a short article entitled Muhammad and Mountain, and the idea there was, you know, is cloud computing, the mountain, going to come to Muhammad, right? So in other words, are we going to improve the performance and all the other factors that prevent cloud computing from supporting HPC computations right now? Or, you know, maybe it's going to be the other way around. Maybe Muhammad will go, right? I hope I'm not offending anybody by using that. But anyhow, so there has been tremendous amount of research, very exciting research done on the mountain to Muhammad side, right? Getting cloud computing closer to the ability to support computations. So, for example, there's a system called, somebody here asked after Abhishek's talk, has ever the cloud computing model been tried on real supercomputers? And it has, right? So there is a system called Palacios, and that was developed by collaboration of different scientists. Peter Rinda, Jack Lange, Patrick Bridges all participated in that. And they ran the Palacios hypervisor. Palacios is a very lightweight hypervisor that deals with many of the performance problems, but also problems of noise and jitter, right, that you get in cloud computing. So they instrumented Actualus and Red Storm with Palacios, and they got results that were within 5% of bare hardware execution. That was very impressive. Those were results on thousands of nodes, right? And when I asked Peter Dinda, why didn't you try more? Well, we didn't get more, right? So there is a bit of a test bed for a large-scale problem there that is right now preventing pushing science in that direction. What is the largest supercomputer on cloud currently created? So I believe the record right now goes to a company called Cycle Computing, which created, I think, the largest, last time I checked, the largest supercomputer was 156,000 cores. And they, you know, every few months they beat their own record in some way, right? Well, 156,000 cores is maybe not enough when we think about the applications that were described today in the morning, right? But it's getting within the same order of magnitude, right? Except these supercomputers are loosely coupled supercomputers, right? So the computations that Cycle Computing runs in them are loosely coupled. They are not what we think about when we think about supercomputer, right? With all the performance and reliability characteristics that such machine needs to have. But people are trying, right? So another statistic, a few years ago, Amazon famously became number 42 on the top 500 list. And of course, that's defined by benchmarks that do not capture all the interactions that we need a supercomputer to sustain, right? But a good effort nonetheless. There is very robust research going on in smart NIC-based technologies, trying to enable the use of InfiniBand with virtualization, so that, you know, InfiniBand-based supercomputer could be sold on an on-demand basis. That's work at the University of Ohio. It's something that I, you know, like to think of. We're 6 months away from getting InfiniBand-based supercomputer, you know, and have been for the last 6 years, right? But I think that something is actually going to happen out of that in relatively short order, and it's going to be a huge disruption when it does come out, right? Suddenly things will become much easier. But on the other hand, on the Muhammad to the mountain side, right, we are building larger and larger supercomputers, and as they are becoming larger, we are beginning to realize that maybe moving in lockstep, maybe having everything tightly synchronized is not such a great idea, right? Failures happen. You have to checkpoint. When you checkpoint, you lose a lot of time. When you restore from checkpoint, you lose a lot of time. So people are increasingly looking into new models and how can we, you know, deal with that size of scale. And it's not just driven by clouds, right? It's driven inherently by the barriers we hit in high-performance computing itself. So anyhow, I think I'm out of time a little bit. I apologize for that. So
yeah, we'll definitely ask you more questions after everybody.
Please.
Yeah. So next, I'll like to invite Dr. Dehan for his views on the topic.
Hi everyone. Hi Roy, Kate, Sanjay, Landon. Thanks for having me here. I would like to dovetail to excellent observations by Roy and Kate. I would actually like to start with a statement that I believe that high-performance computing, like most other areas, will increasingly commoditize. I think the general purpose and high-performance computing are converging. Now, having said that, the very high-end laboratories, national labs, will still run supercomputers in the same way as the largest banks still run their transactions on mainframes. But bulk of the rest of high-performance computing users, and there will be, I believe, increasingly more so, will run on commodity hardware and software. I would also like to expand horizon a little bit more than what Roy said about SSDs or what Kate said about the costs of checkpointing. If we go a few more years out and look at new non-volatile memory technologies, they will enable much larger memories and will eliminate some of the bottlenecks in terms of memory. Similarly, the checkpointing will be relatively fast. It will still be costly for, at that time, computers, but much cheaper than today. They will also enable other benefits in terms of power savings, which I think will be one of the biggest bottlenecks from a technology perspective. I completely agree with Roy that memory is the biggest problem, even though that while Abhishek and I were doing research, we identified interconnect as the biggest problem, and it is the biggest problem because one needs to move the data around. So ultimately, and originally, it's all memory's fault. But one of the new technologies, photonics, comes to rescue there, I think, and it's increasingly getting closer and closer to processor, so-called silicon photonics, and I believe that will help quite a bit. Roy already mentioned new types of accelerators, FPGAs, GPGPUs, and others, which will enable very focused, dedicated hardware to solve specific problems, which may sound like departing from commoditization, but I think it will only enhance and will also help with power by having much smaller power footprint, even though we'll probably be forced to, turn on and off these parts of the silicon, so-called hard silicons that won't be running at the time, but can be turned on once you recognize that specific applications are needed. I would also like to think about cloud as a business model. There are technology definitions, but there's also a business model. And the question is, for me, when I think about it, okay, so we have HPC in the cloud. What does it mean? I mean, we can put supercomputer behind the cloud interfaces, and there you get it. You get the same thing. But what you can't get is the business perspective, and that's where Abhishek and I try to evaluate a little bit more. Supercomputers are already very highly utilized. When we spoke to national labs, they said it's not only 80%, as Roy mentioned, but in their case, even close to 100%, because researchers need to use it. They continuously feed the pipe. If you put it on the cloud, in the cloud, assuming that Amazon is willing to undertake risk of, millions and millions of dollars to invest in it, probably close to the billions, it's a risky value proposition for them. So the transition of HPC to the cloud is going gradually, from the low-end users to medium-end users, and as we already said, the high-end users probably will always remain on the supercomputers. Now, going up the stack from the hardware, there will be, I think, as already pointed by my excellent predecessor speakers, there'll be need for the change for system software. Non-volatile memory will completely eliminate big part of the stack for device drivers, for the buffer pools, for all kinds of things. Now non-volatile memory will be possible to access in a byte accessible format. And the same thing with interconnects. There'll be newer, much more efficient types of RPCs and things like that. And then going up, which is really the critical, and I think Kate touched quite a bit on it. She carefully chose not to use another fluff word beside cloud, which is Internet of Things. But all these sensors are really going towards the Internet of Things. And, there's a lot of fluff there, but there are real problems as well. And I can name just a few. Sensors on the planes. If you can connect all these planes with the sensors, you can avoid many problems. And so many times when I got on the plane, got off the plane after half an hour, because it was just a little problem, engine didn't start. They could be in the position to detect that across the whole fleet, and maybe more. Another one that we look at HP is the security analysis. All these packets that come, create a huge demand on analytics. Part of it has to be in the real time, just like Kate said about these sensors, others on the back end. Then smart meters, and I can go on and on. But ultimately, I think between commoditization and then evaluating business models, these kinds of things will determine the future much more than the technology. But I'm really glad as a technologist as well, not just as a manager, the technology is marching ahead with new and exciting things for all of us to look at.
Thank you. Landon.
Test. So Landon Kurt-Noll here. So I was asked to come in and be a little bit of iconoclastic regarding supercomputing, the supercomputer industry. So I'm going to talk to you about computers as tools, benchmark madness, computing smarter, and being creative. I think one of the things you really need to remember is that computer is a tool to get something done. So use the best tool in the best way to solve your problem. So people say, can you do HPC in the cloud? Well, if the cloud is the only thing you have, HPC in the cloud is your best tool. So use it in the best way. If you have a combination of things, and there's certain tools, a hammer can do certain things with carpentry where a saw or a chisel is needed, but you can use one inappropriately. You use the tool to solve your problem. Recognize that computers are tools in order to try to solve problems. There is in the supercomputer industry, the people who build supercomputers or sell supercomputers and people who buy supercomputers, there's this disease about benchmarks. And people actually architect to solve benchmarks so that people can have bragging rights. They can go to a bar and say, my computer is bigger than your computer. And really, there's a lot of machines get architected for that reason. And I applaud those big machines that refuse to contribute to the top 500 as a way of saying why. Because the benchmark is not necessarily the problem you want to solve. We submitted to top 500 the ultimate LINPACK benchmark, where we taught GCC to recognize LINPACK and output maxint. And they said that we were being naughty word, and we thought we were being treating it appropriately. That is, you can compute without the fastest CPU, without the most memory, without the minimal latency, without the most number of nodes. You can actually do real work without having the biggest, or even the second biggest, or even the 100th biggest. And this comes to my third point, which is it's much more important to compute smarter than harder. Smart computing with limited resources can outperform big machines just blasting away. Every time I've had a world record relating to number theory, relating to computation, I've never had access to the biggest machine. I had effective use of the machines that were available. I mean, at Amdahl, we had a single Amdahl beat the entire world idle time on Crays, all the manufacturing stuff, and beat it by something because we were smart in our hard computing. We just simply didn't have a bigger hammer. So the cloud can give you some access to those things. Even if it's not the bigger hammer, you can still do great work. The work that Dr. Goddard is doing in FEM, doing some of the largest simulations published in literature on an embarrassingly small machine, because they're really clever about how they use it. So being clever is something, and cloud can, cloud, because it's not some giant machine, you're constraining your resources perhaps, so you can make up for that by being clever, and humans can be quite clever in that sense. Then the problems we have also need to be considered more creatively, rather than solving embarrassing parallel problems of sensor arrays. In astronomy, we have this device called the universe that we need to read. And reading is a problem because it's a big universe out there. So something like the Square Kilometre Array Telescope is being envisioned, where the network just to read the universe is going to dwarf the bandwidth of the internet by about a half order of magnitude, not order of magnitude. And we're talking about things where we have to be very creative on how we ship the data around. The machine will probably be producing about a terabyte a second of science data, which we hope to collect for about 30 to 40 years. And we need to store that, and of course it's a multinational problem, which means different companies want their copies of the data. So how do you build a network like that? Well, probably the way we're going to end up doing is starting off with solid-state disks and container cargoes on a ship, and the ship will come into Perth or come into Cape Town, load up, and then it'll go around in ports and dump their data, and that'll be our data pipeline for a while, because astronomers don't need immediate access to things, or if you do, you put a computing at the beam. But one of the things about this type of telescope is it's going to change it from, that's my telescope time, I have the data, it's mine, then I publish it, to the telescope is a machine that's going to produce data that will be mined, and that the real astronomy is going to be done by people putting computers, connecting into the data stores and mining the data for valuable stuff. So it changes the way, these kinds of interesting things really change the way you go. So, so again, remember, computers are a tool. Use a tool to solve a problem. Don't be hung up about benchmarks. Compute smart and be creative on the problems you're looking to solve. That's it.
Otherwise, I'll just read from them. And I would like to. What do you think? Okay. So I will adaptively overlap. Okay. So I think one of the distinctions that I see emerging is between science applications and engineering applications. So we see the supercomputers at the national centers and so on, and we're going from petascale now to exascale. Those computers are focused on largely on science problems, very few engineering problems. I don't know if you see it that way. And so for engineering problems by mid-sized companies and so on, well, cloud might be a pretty good platform if, like Abhishek was pointing out, the classification is you target the cloud platform for the right sets of applications, and like Landon pointed out, you be clever about it so that you can stretch the class of applications that can run on that platform. Are we okay with that? Yeah. So so I wanted to say a couple of things. That's the first point. One of the issues that comes up is the HPC applications are tightly coupled, fine-grained, lots of communication, and so on. Well, there are a couple of things here. One is the latency and overhead are two separate things. High latency platforms are okay for many applications. I'm reminded of the thing that we did with Greg Koenig's work many years ago, where we set up a cluster here and a cluster at Argonne. And there is, I believe, a speed of light latency of a couple of milliseconds there. Actually, coast from here to the East Coast, 3-4 microseconds, some milliseconds. And you can tolerate that for a fine-grained, tightly coupled fine-grained application such as molecular dynamics, whose time step at that time was 5 milliseconds. So how can that happen? Well, there is some local computations you can do while you're waiting for remote data, and then when you send your response back, then again you do some more local computation. Sounds familiar? We do that for astronomy applications on supercomputers. So by having latency-tolerant algorithms and the runtime, of course, we can actually deal with that. Overhead must be kept low, though, and that is a challenge for the hypervisors and other virtual machine things. And I think that's being met as we move forward, as we'll probably see. The another interesting thing in the cloud environment is that maybe because of demand, maybe because of a variety of other reasons, it's a fluid resource. The number of nodes available keeps changing. The rate at which they are available keeps changing. Maybe you want to be able to take your job and run it on fewer or more nodes as the rates change, or conversely, the the manager, cloud manager, might want to tell a job, hey, I have some high priority job. Would you vacate half of your nodes or 20% of your nodes? Or here I'm giving you 20% of the nodes. Those kinds of things require the shrink and expand capability that we heard about from Abhishek and from Suraj and other talks earlier. And those would be very nice. And of course, adaptive runtime systems fit well there. One other thing that I want to just kind of, I was reminded of as I was thinking about this, is our Faucets project. This was done somewhere between 2000 and 2004. The code still exists. We try to brush it out from time to time. The idea was submit once, run anywhere. So basically the idea is you submit the job, and the infrastructure will figure out, and you have a quality of service requirement specified with the job, and accordingly the system will find the right cluster. You can call it a cloud, going over the cloud, find the right cluster, and submit your job there. You don't even have to know who is running your job. But you can still attach to it. You can even live interact with your job once it is running through an intermediary. And then how do you pick which one runs it? Well, through some kind of a bidding system. And there's a very interesting economic market type models there that we worked on for a bit there. And so someone needs to generate a bid. Of course, market makers need to, it's like select the right one for you and so on. So it can get into an interesting model there. So that's one of the ideas that comes to mind that might gain currency again. I want to mention a couple of additional issues that come up here. I think our ISVs are lagging way behind in this. If you look at the software vendors and how they charge for usage of the computers and the way they license their software, it's per core. And again, if you have a fluid environment like cloud, they have no idea how to charge and so on. So licensing and charging models for HPC independent software vendors, that's an unresolved issue in my mind that needs to be solved. I think protecting proprietary data is another important issue, but I think that is being addressed and solved in a variety of ways so that people start trusting other people's computers to run their really important data. So I think I'll stop with that.
I should point out that I think, for a Charm++ relevant comment, that Charm++ holds a lot of promise for being able to do computing smart. A Cisco executive asked me, well, what's this Charm++ thing? And I said, well, essentially it's code to keep the physicists out of a cache lock. And that's one of the problems with a lot of code. There's a bunch of code written for the Cray-1 cache lock into an architecture that no one's been able to change because it's a 500,000 lines of Fortran with no comments, and it works well. And so they say, well, just emulate a Cray-1 and we can continue going forward. So instead to say, the physicist needs to do, what do you need to do science-wise? Oh, I need to do cross product of these matrices. Okay, now you tell me that, and let some computer science people figure out how to schedule it, and then pick the right tool for the right jobs, and with the tool begins to suck or dole its edge, you move it over to something else. And that's sort of the things you're going to find in the cloud that I think Charm++ can help. People that are operating at the MPI layer aren't doing not much better than writing assembly code in terms of they're sending stuff back and forth. They're not at a high enough level, and they're not able to adapt to a case. So you really need to be able to say, I want to have a heterogeneous machine that changes in time and space and solve my problem, be elastic in my computer. So that's all Charm++ sell.
Let's thank all the panelists first, and then we'll open the floor for questions. Okay, questions, please.
Comments.
So I guess just a comment or an observation from my experience is that clouds, or I should say clusters, are made usually out of commodity equipment, and commodity equipment tends to have a much higher failure rate than its HPC counterpart. So there seems to be a crossover point where the cloud actually costs you more money because it's constantly down, and the HPC system isn't. What's sort of your comments along those lines?
So there's a wonderful example where for the accelerator out in CERN, they actually store the data of one of the experiments using Hadoop or using HDFS. And the reason is because they couldn't get enough storage cheap enough for the project. So what they did was to buy lots and lots of disks and lots of machines, and they duplicated all of the output. HDFS worked very well for them, and this is how they actually managed to keep copies of what had happened in the experiment. Now, of course, the problem is they got all this data and they have to process it, but they did manage to collect the data that way.
And I think relevant to this university, I had the pleasure of using the LAIAC 4, and we managed to get a lot of time in LAIAC 4 because we wrote algorithms for 16 processors because you could never get it to work with 64. It had 64 machines, and it was a very lucky day when all of them ran perfectly. So we got time where codes were written for 64 that couldn't run. We would say, well, we'll run, and we got in under there because we were actually stealing time rather than getting allotted by grants. So one of the things as well that you need to be aware of is not only mean time to failure, but mean time to error. If you take an Intel CPU, and let's say you're doing something as simple as it's just going to use the cache and registers and do ALU, arithmetic operations, how long do you think you compute before you get an error where it says 2 + 2 = 5? You'll find it's embarrassingly short. Now, we had one process. I have to be nice because they're a partner of us, so I won't say the number of weeks, but it's an embarrassingly small number. So if you expect perfect computation, you're going to be sorely disappointed. So you need to build code that's adaptive and is fault tolerant. When I did my seminar on how to find a new largest known prime, I say expect 70% of the time to be checking errors and rechecking errors. You only think new problem 30% of the time. Now, Intel will say, when we showed them one of the chips and how bad it was, error rates, their response was, quote, Windows has a shorter mean time to error. We're not the weakest link, so don't bother us, right? So don't expect, so these commodity hardware, and by the way, one of the things that happens, the cloud does to, HPC does to the cloud, is the cloud depends upon you running in a green environment. That is, they set the BIOS settings so that it'll drop speed and try to be as green as possible, because part of the cloud economics you're talking about is over the issue of, or I guess that also gentleman is assuming that you're not consuming high power. When you drive it in HPC loads, you're much faster mean time to error, right? When you overclock it, then you can kiss your error rate goodbye in a bad way. So cloud providers are going to find, when HPC applications start running on them, that their economic models are going to be disrupted. Machines are going to break more often.
I just wanted to add, Chris, that if you find those cloud machines that err more frequently and in fact stop, especially the fail-stop failures, we'd like to know about them. The problem is, since about 2003 or so, we have been doing work on fault tolerance in my group. And every time we said petascale machines are going to fail very frequently, whatever. And so, and then there is another component in the field, another group of people that say, no, engineers will fix the machines; they will never fail in time for your simulations to finish. And so we developed this research, and in fact, right now we have, like you heard from Xiang, this automatic system that if a job is running and one node dies, it will automatically. And in fact, we should have brought the small cluster of these BeagleBones here. You could actually just plug out one of those things and it will keep running. So we have those nice schemes there. We just don't have a good place to run them on because we don't get failures enough. We have to plug things out, inject failures, whatever. And clouds may be a very nice test environment for that then.
So just a quick note, you're perfectly right. It's Beowulf all over again, right? We're building from off-the-shelf components, and they have much higher failure rates. But we don't really know how high, right? So we don't really have data from those big cloud providers saying, this is what happens, this is how often we fail. And to speak to Sanjay's appeal, right? If you find the failures, let us know, right? I actually looked at different papers to see if somebody has reliable data on that, and not so much. And so I started talking to Google, and I started talking to various cloud providers about making such data available. there is actually a group that I'm participating in founding called Open Big Cloud that will have a workshop next week, and that will bring together people from both academia and industry, and primarily industry, really, to look at extreme phenomena in the cloud, right? So look at big compute in the cloud, look at big data in the cloud, and what we cannot do right now is look at those things very effectively because we simply don't have the data, right? Because a lot of the cloud providers don't share the data, but yet, you know, fault tolerance and reliability is one of the hottest research topics, I think, in the cloud for the very reason that you mentioned, right? If you're going to provide a reliable supercomputer, you need to know something. And so I think that the place to start is having the data.
So if I may add a couple of things. Someone made observation that things can fail quite a bit in the cloud. That is true, but that's really the question of scale up versus scale out. And I think the industry has more or less decided to go scale out for two major reasons. The first is cost, because it's much cheaper to go scale out than to develop high-end machines. But the other frequently overlooked reason is the scale. You know, if you look, but that has to be qualified, scale for certain applications. So most of the applications are now designed for scale out, and they go, you know, over hundreds of thousands of nodes. And you cannot afford these kinds of machines for the scale up, these number of cores and memory, etc. And however, to overcome the issues of the failures, one moves failure tolerance at the higher and higher level. So as Roy was pointing out, the disks and machines and servers fail. No one bothers to replace them because either storage or the applications or the servers. For web servers, it's trivial, but many, many more applications are just being designed to tolerate these failures.
I think also you raised a very good point on the issue of economics. And one of the things you say in terms of the type of problems you're trying to solve and how they deal with economics, you know, there are certain HPC problems that I call, as long as the result fails to suck, it's good enough. And if you're simulating the Big Bang and like the 1 second to 1,000 years after the Big Bang, and what you get is universe-like, then you're satisfied. You can have all kinds of errors inside, and it's good enough. There's another class which is the needle in a haystack problem. Let's say you're looking for the DES key or you're trying to find a hash collision. As long as the errors occur on straw and not on the needle, you're okay. And then there are the third, more unfortunate times where it's perfect, where you're factoring a number, doing a probability proof as an example, and where a single bit error, you know, wastes the entire calculation. So sometimes you might be able to handle the cloud by trying to move the kind of questions you ask over to the it fails to suck as opposed to it's got to be perfect as a way of handling reality, which is messy. It'll cost a lot less if you have the first rather than the last.
While I wait for the next question, I just want to tell Landon, Blue Waters, one of the most powerful academic computers in the US, refused to participate in the top 500. No top 500 entry for Blue Waters.
I was a system programmer for ILLIAC 4, and I'm glad that somebody actually got to use it for something useful.
Hey, how do you know it was useful?
Right, yes. But one of the big changes between then and now, ILLIAC 4 had a 1,000-bit wide memory I/O bus. Split 1,000 bits every second, every microsecond. It was, you know, the skew on that is sort of amazing. But they made it work, I think, only for 16 processors. But and back in those days, for supercomputing, they didn't seem to worry that much about. In some ways, they didn't worry about reliability. Seymour Cray said parity is for farmers. He's not going to slow down his machine by doing any parity checking. And he's going to have a 60-bit word, so he doesn't have to do any really fancy floating point arithmetic. And I think some of his machines didn't even have a divide.
Yeah, well, the early Crays just had a reciprocal approximation unit, and when I did the Merce N prime test on the first Cray 1, I didn't get the right answer, and it turned out there was a bug, there was a bit error in the lookup table and at serial 13, but there's a lot of physics code that was written for the previous machines, and if you went and fixed the hardware, you broke the code. Right? And then there was machines that were not serial numbered but were in a TLA, and they were trying to do stuff, and they had to decide do they want to fix or not to fix.
Right.
So it's errors in classical computing is theirs, but again, I think HPC is trying to solve problems that are bigger than one machine can handle, that last longer than one machine will correctly compute, and will produce more data than what one convenient little storage pod will have. And so when you're dealing with those kind of problems, you're just trying the way to work it. In the case of the ILLIAC, it was use maybe 2 pods of 16 and vote and retry when you got an error, rather than assume you get slightly faster by assuming all the processes work perfectly all the time.
Right. Yeah, we the Coordinated Science Lab got a CDC 1604, is that the right number?
Yeah.
And they emulated ILLIAC 1 on it, and to test their emulator, they ran the hardware check paper tape through, and they found an error in the CDC hardware.
Sure, and so we one of the excuses that number theorists have in looking for doing like computational problems is we do hardware checking, right? If you have a perfect problem, I mean, this is a thing. If you want to get time, get idle time on people's machines and check out their hardware and help them report hardware bugs, OS bugs. Do you think that the virtual machine is going to always swap in the right page of memory? If you're not marking your pages of memory and looking at them occasionally, you'll be disappointed. So build fault tolerant code, and I think Charm++ has the ability to not only schedule the right resources, but say that thing seems to be kind of giving us too many wrong answers. Let's avoid using that node and move stuff elsewhere.
Right. But it strikes me that nowadays, with things like Thunderbolt to connect that are very fast, you could end up almost putting together a network that satisfies the way your data exists.
Yeah.
Since you don't need a memory bus, or we're getting so fast we don't need memory buses, and that sort of just changes everything.
I was going to say that I think if you push the envelope, you'll always run into the reliability problem. And so nowadays what we have to do is to build machines or build architectures, build software designs that encompass reliability, because you can't just be guaranteed that the underlying system gives you that.
And of course, unfortunately, if you're actually doing something interesting, you're pushing the envelope. Yeah. And that's what research is. So you just assume the universe is not very perfect, and you just have to live in that universe.
I think what's interesting about COTS is they start out believing that their universe is not very satisfactory. Sometimes we make the assumption if you spend a lot of money, you get something that actually works, which is a big mistake.
So I don't have a question, but really a comment to drive discussion. So many, many years ago, I'd heard about this cloud thing, and I was like, I don't know what it is, right? And then I have to write an NSF report, and they said, well, you're getting all this computer time. What's it worth? Okay, I got 2 million hours on XC. What is it worth? Because they want a dollar amount. The NSF, like, what is it, right? So, okay, I used the cloud. I went to Amazon, and I looked up something appropriate, and at least it gave me a price, right? So I'm like, okay, I guess people run here in the HPC, in the cloud, because they offer this service, right? So then a few years went by, and I've noticed 2 things. So I'm a university researcher. For my PhD, I used many supercomputers, writing codes. These are these very regular machines like Crays. And then I got out of the business for a while. Now we're trying to hook up with Charm++ to write applications in a different way. But from a researcher at a university viewpoint, here's this computation I want to do. I could try to run it at a national supercomputing center. They are severely underfunded, so I get about 1/6 of my compute cycles I use each year in the national supercomputing centers, although I'm 100% funded by the federal government.
Yeah.
Okay, so what am I supposed to do with myself? So luckily, the provost at my university has decided to spend money on computers. Okay, so they have a big cluster for a university, and I get just access to it, and I just suck up all the cycles, and as you say, steal cycles that are just sitting around. So we get our work done. But this is a very expensive proposition for them. They're going to probably start charging user fees. And we will never be able to pay this from our grants because the federal funding is at most stable, but probably decreasing. So they're just going to squeeze us. Where are they going to squeeze us? I don't see any other place than telling us go buy cycles from Amazon or something like this. I'm just trying to have a very pragmatic view of the pressures on a university researcher with dwindling or fixed at most funds, insufficient national resources, and a university system that will fundamentally push you out because it's too expensive for them.
One of the things I think that you want to look at is try to get them to get job schedulers, resource schedulers that can handle background tasks and say, okay, I've been granted this much money, this much time, but if there's extra time, let me come in and backfill. The other thing
they want to charge me money for that.
Yeah, the other thing is try to show if you're going to be contributing to the heat death of the universe, show that along the way you're contributing value is another way to handle it.
I like that, heat death. I think what you've described is a really big problem for all the universities and for probably lots of other research institutions too, that there isn't that much spare cash in the economy. And if you look at the economic cycle, you know there's going to be a downturn in a couple of years, and that's going to hit us really bad. So you need to plan for that. Actually building systems for universities that provide you critical infrastructure, if you like, for your research, but do not cost an arm and a leg, and sort of take all of the best demonstrations out of the cloud industry and apply them to the way you're providing those facilities, I think is something that we should all be learning how to do. You shouldn't be having labs with different machines in a university. Maybe within the big 10 universities, we should be sharing one huge computing infrastructure. And perhaps we should be organizing that computer infrastructure so it's simple enough that there's only a couple of people actually managing it. We really need to rethink how we're providing those computer facilities, and maybe we don't need 90% utilization of those machines, but what we want is a really low cost 70, 60 something percent. We need to find that out. And this is one of the reasons I like Charm so much, is that it's flexible enough that you can play with the infrastructure and still write your codes, still get your codes to work without binding it to a particular infrastructure. You can get the infrastructure adaptive to what you're trying to do.
I just wanted to say, for a while I thought about this. National centers serve a couple of different roles. They provide cycles. They also provide consulting and expertise. They are reservoirs of expertise. That second function, if you can separate it, refactor it, then if you think about cycle supply, then the one way in which NSF and other agencies could deal with this is by basically not funding cycle providers directly, like TAC or Texas or Waters. What am I saying here? But anyways, okay. But in some future world, but then directly, then just give people money for compute power, and then they can buy their compute power from whatever provider they want. And IBM, Cray can build their supercomputers and charge on per use basis. What interesting things will happen once this is a market like that? Well, jobs that don't really require tight coupling will go the cheaper route. Jobs that require, even within supercomputers, I believe there are maybe 2 or 3 separate categories of applications and machines, like the ones that require bisection bandwidth, full bisection bandwidth, versus the ones that don't, ones that require a lot of memory per core versus some that don't, and the market will choose and apportion resources between these different types of computers correctly if we were to do that. I think that will be an interesting thing to do. I don't know the funding agencies will go that way, but
Just a one small point to pick up on things that others said earlier. One thing to realize about the resources in the cloud is that they're on demand. This is a very significant difference from what typical computational center gives you, which is batch access. And so the point that was made before about let's find a way to run in the background, well, cloud providers provide such a way for much cheaper than the on-demand cycles, and Amazon, for example, calls it spot pricing, right? That means that you get resources that are somewhat volatile. You don't know when they become available at the price you want or when they will be yanked away from you, but you pay hugely less for them than you do for those on-demand resources. And that goes back to Sanjay's point as well, which is that market will find the price. You don't need really powerful resources for every single computation. Market will find the price for resources that are maybe not as powerful as others might require, right? But that goes not just to the shape of the hardware, but also to how that hardware is made available to you.
And Cisco, I won't name them, but Cisco has a large cloud providers building stuff with our equipment and our computers. And one of the things that this cloud provider is going to be that power is also power and cooling, which means if you're an HPC job and you want to rev up the memory and use lots of cooling stuff, you're going to get charged more than if you're a job which is gentler in the CPU. So one of the things that Charm++ could help someone do is to not bang the CPU quite so hard. Your error rates might be better, but also your power costs might be better as well. So working on power consumption as a property, as well as error recovery, is something that I think Charm++ can give people that ability to let the computer scientists help the scientists use the hardware.
In fact, there was a talk yesterday on that, and we have quite a bit of work on that. So I suppose cloud would be a good place to test those ideas with optimal allocation of power and energy for temperature and cooling. Yes.
All right. So you guys were talking about fault resilience, and we need to build it into the algorithms, and that sounds wonderful. Charm, it has some capability in that respect. But it's still at a very coarse level of, yeah, this node went down, at which point, yeah, you can tell it. For your prime factorization, you have a way of testing, did I get the right answer? But if I'm solving some nonlinear PDE, how do I know if I'm getting the right answer back?
This, of course, is a hot area of debate within HPC now. And say last week at Salishan conference, there was quite a bit of discussion about it. But there are several ways. One is, for example, if you have some kind of a field, then an error in one place in that field is going to only delay conversions. You can do it, think of it that way. So make algorithms that tolerate small failures that way, and the variables that are kind of important, we'll store them in some reliable way, maybe 2 copies or something like that. The other alternative was some multi-grid like approximation. Suppose you have a field type value again for every point in space there is some value. Well, represent a reduced representation of that for every 8 points or for every 64 points, put an average value there, and then see if any one of them are significantly different than that after every checkpoint, and that will tell you something went wrong here. Then you are going to do some approximation to the outlier, and that will maybe again have some impact on convergence. But there are methods of this sort for values that are just generally describing some floating point field over space, for example.
I think Dehan had some points regarding. Want to say something?
Well, I actually had for the previous. I don't want to interrupt this discussion.
No.
Well, the previous question was around whether you do it in the cloud or buy equipment. And interestingly enough, when we were building OpenCirrus and we bought equipment for UIUC, Indy Gupta and I have done analysis of, was it the good idea to buy the equipment, or were they supposed to go to Amazon? And the answer was simple. It is all function of the utilization. there is always a break-even point in this spectrum. To one point, it's better if you, for short-time use, it's better to just go to Amazon. But if you're planning to use equipment for long-term, then it's better to have your own equipment. And utilization moves that earlier or later. If you are utilizing it heavily, then that break-even point comes even earlier, and you should buy your equipment earlier. It's a very simple math.
I do have a rider to this, which is I think one of the things that we need to be able to do is be agile in our HPC, in our computations and so on. Everything's changing. Even the way that we think about data and its interaction with our computations. So we've heard about collecting huge amounts of sensor data and putting that somewhere. Well, we don't know how to do that, really. We're starting to do it. We've got Storm, we've got all sorts of other things, but we don't really know how to do that. What we need to do is be agile, and we need to be able to adapt. And one of the things that the cloud technology brings to us, even if we don't like to admit it, is that it's designed by people who get, perhaps one might say, poor programmers, but certainly not really sort of top-notch HPC programmers, but they're doing things in parallel, computing things that the companies, whatever, need to be done, and they're doing it very efficiently. If you take Amazon and you try and implement your own algorithm on Amazon, you're likely to cost yourself a lot of money because of the mistakes and the time that you use in trying to get your algorithm right. Having a local machine is a lot cheaper, but also having the right software development techniques would be even better. So I really would think one of the keys to all of this is to build your software development so you can change your mind, so you can be adaptive, and you can move from one platform to another.
One of the things on terms of reliability and simulations is doing something like you're simulating Jupyter. I try to simulate more than one Jupyter with more than one algorithm, because more likely the error is in my code, not in Jupyter. And if there's like CPU errors or something, you might see that one of the three simulations has some spots where you can sort of outvote or retry that area. But that's another example. You have to use more resources in order to gain greater perfection, but that's what the universe has you do.
I wanted to pick up on the point that Roy made and that Sanjay also made, which is that clouds are a disruption, and they are disruptive in the sense that they renegotiate the roles and the established tools that we have to accomplish things. So one thing is, when you go to Amazon, you're buying not just the resource, but you're also buying certain types of maintenance of that resource, right? You're buying the floor space, somebody to maintain it, keep it running, and so forth. But on the other hand, you're not buying what you used to get from computational centers, is somebody to configure the resources that you're running on, right? And this is now something that you have to either provide yourself or create a new layer of system administrator or a new layer of services that will be operating within your institution and providing those things. We don't, right now, those boundaries are not completely clearly understood, and we don't have things that do those things. The other layer, of course, is the software, right? How do we deploy those virtual clusters reliably? How do we adapt to failures by redeploying more machines, for example? How do we contextualize those virtual machines so that they securely find out about each other and can operate as one unit, and so on and so forth. And unless you have that software, you will spend a lot of time developing, and not just a lot of your effort time, but also a lot of the time that you're buying from Amazon to run those things. So, while cloud computing provides compute power on tap, at this point in time, it sometimes seems like every time you want to turn that tap, you have to call a plumber, and that gets very expensive. And this is a cloud computing issue right now. It's not just HPC in the cloud computing issue, right? This is very widespread. So solving it would amortize pretty quickly, right? Would have benefits for all sorts of applications, not just the HPC applications.
So interestingly enough, I've heard different perspective about ability to reconfigure, and that exactly came from the national labs. That with big supercomputers, you can't really touch and reconfigure anything. If you do it in the cloud, you can make changes to your virtual machine. You can put different kinds of libraries, play with it a little bit more. But otherwise, I agree completely that the future will really rely on how we program and use these massively parallel hardware architectures. So new programming models, new algorithms, be it for Jupiter or for other planets or universe, I don't know, but
sure. Well,
outside of my scope.
And you also raise a good point. I mean, Cisco has put a lot of effort into its UCS product, its computer product, and we built computers part because we thought that one of the places you can put the brains is pull it out of the kernel and into the network, and let the network control the computers. So part of the thing is, as well as we have customers that spend a lot of time just bookkeeping, keeping a spreadsheet of all the nodes and who's doing what and so forth. That's a non-trivial amount of time. So trying to allow people to have generic machines that the network can configure on the fly is much better. You build a data center by wiring it once and let the network redefine your set. Now that comes with a cost, but the value, if you're talking about amortization, economic value is much better. And the people who understand the total cost of computing, or if you're a researcher, the total cost to your grant, will appreciate a machine that's easier to reconfigure, easier to administer, and easier to manage.
And I apologize, I will have to leave now because I have another conflict with the meetings. Thank you very much for having me here.
Yeah. So.
Thank you.
Bye, Dan.
Bye.
So just a quick note, I think that we all agree as to that. So half of the users I work with tell me that they want to configure their own virtual machines, and the other half tell me that they don't, right? And this is not really a contradiction. They all would like to have as much control as possible over the resources. It's just that some of them do not have the skill and expertise to configure them themselves, right? So, right. So what's really needed is a role as somebody who can work with them on that. And yes, it used to be impossible to do that in large computational centers. They always had to strike a balance in the environment that they provided between various conflicting requirements of users. And when you have a virtual machine, you can do that much more easily, but you still need that support.
Yes, I mean, so I should. So what you said reminded me of a operating system. You need some reconfigurability stuff happening depending on what the users want. I think it was also start with CH. What was it? Choices. or I did a thing called choices, an operating system. And I think I would like to personally, although I know we are running late now, but the US NIC we talked about commodity. Components being used more and more in HPC. Dejan made a point about only a few people can have these white elephants, but majority are going to have systems built using the commodities. And in fact, I was very impressed with the US NIC. I don't know how public those results are, but maybe you could tell a little bit about that.
Thank you for that sales thing. I'm not a salesperson, so you have to sort of prompt me to do it. But Cisco has some interesting networking technology where essentially it allows for processors to directly control the network device rather than. And so we have these network cards where you can have 256 virtual Ethernets, right? And depending upon what PCI addresses you talk to, Ethernet A, B, or C. Well, by bypassing the kernel and allowing a user process to directly map into that memory, a user process can directly send and receive a message and get very, very low latencies. And then by doing that, double bypass through a hypervisor, you can have jobs running on a virtual machine, running on a hypervisor, talking to a slice of hardware that then builds, can perform their networking. But these kind of virtual hardwares, virtual Ethernets, allow people to build networks based upon what they need. The old classic ways, you got two Ethernet cards or two plugs, and so you put this stuff on network A and this stuff on network B. When you have these virtual networks, you can say, I need a network to do my administration. I need a network to launch jobs. I need a network to do backups. I need a network to do telephony. I need a network to do, MPI-like things. And you can build your networks on the fly, virtual networks over the Ether network quite effectively, so that you're in control of how your network's configured rather than the hardware's control of you, or at least it minimizes it. But the main thing about USNIC is its ability to essentially have processes directly send and receive messages. The next generation of NICs are going to have even smarter processing going on. I'm not allowed to talk about that, but you can imagine doing some more intelligent things in the actual network devices can accomplish stuff.
You may not be able to talk about your stuff, but I can certainly talk about SDNs. You're going to see a network revolution going on, and we're going to make networks a service just like everything else. So if you want some fancy network, you can just design it with software. This is just around the corner. So this is all very exciting. I'm not sure how you program it in Charm++, but I'm sure at the next meeting there'll be probably somebody saying this.
So if I may interrupt, we are running late, and in the interest of time, we'll have to end the session. But I'm sure you have lots of other questions, and we can ask those questions during the break. And let's again thank the excellent panelists.
The break right now, but I just want to remind you that dinner is at a group of us are going for dinner, and we'll assemble maybe at the base of the stairs on the ground floor at 6:30, because we have 6:30 is the reservation, so I think we assemble at 6:20. 6:10, yeah, 6:10, 6:15 we should assemble downstairs, then we put you in the cars and we go there. So 6:10 or to 6:15 at the base of the stairs. 5:30 the last session should end. We are behind, but we'll see how we end up going there. Any other announcement? Yeah, and even if you didn't write your name in the morning on the sheet, that's okay. Just tell me, I'll increase the count, and you can come for the dinner, right?